right? A structure is made up of several things, and we just more or less extract that. So this point is made up of these three floating points. And here we're saying we're giving from that point names to the members. So right here we can just say X, Y, and Z. If we had not had this structuring, then we would have to write P.X, P.Y, P.Z. But there is a little gotcha that you sometimes may notice as this makes a difference. This is not actually declaring these variables X, Y, and Z. It is declaring only one thing. It's this one object, the const auto object that is, in this case, a copy of P. So you're creating a new point there. You're not creating the X, Y, and Z. And this, every time now you mention an X, Y, and Z here, that is just a shorthand to actually this member. It doesn't, in this case, it's using the same names. You don't have to. You could call them A, and then A would be a shorthand to temp.x. It's positional, right? It's not matched by name. The interesting thing here is that you don't have to invoke the things that might be surprising because you're still acting just on the outer thing. Here we're invoking the copy constructor of point, but you could also just take it by reference or const reference and then just reference this thing and get access to the members with a shorter name. You can destructure also arrays and class types. Normally in class types, you make your data members private, and then you would not be able to do so, right? If you just take the struct here, turn that into a class, then the default will be that the members are private, and in that case, you could not do the destructuring. For tuple, also, what it stores internally is private, and actually the std tuple in lib standard C++ stores it the other way around. So the first object in memory in lib standard C++ is char, and then it's an int, and then it's a float. It's because of the recursive nature of how it's implemented. But what we're doing here is we're destructuring in the end into the float, integer, and char. So there's an extra interface that allows this to work. Anyway, for std tuple, it is very, very helpful because otherwise it would have to write like this get 0, get 1. It's hard to read. This is the kind of code that when you write it, it's somewhat okay. You're in the mindset of I'm using this tuple and this positional parameter, but when you get back to the code and read it, you're like, what is this actually referencing? And then just figuring out what this is doing is so much harder. So if you ever have to interact with tuples or something like it where you cannot have a good name to the members, destructuring it and giving names is very, very helpful for code quality. The std tuple needs to do this kind of opt-in to structured bindings because by default, the type itself could not be destructured. The simplest way is if you want to opt into structured binding, just write an aggregate like the struct point that we had in the beginning, just a simple C way of declaring structures. I would recommend that often just to do this. But if you ever have a class type where you want to do it differently, what you have to do is you have to specialize tuple size, tuple element, and a get function. If you specialize these three, then the language facility for structured binding says, okay, you can do it, and will provide it like you defined it here. So you say my class has 4 members with this. It's just derived from integral constant. Here you have to have a type member. Depending on 0, 1, 2, 3, you need to then provide what is the type of that positional data member. And then here you provide actual access to that. And through this, you can also enforce read-only access. Whereas with a normal struct, everybody could just also get a reference to it and modify one of them. You might want to have an interface where you can destructure but only read. And this is something that you could do here. Also interesting, sometimes you don't need all of them. So if we have like this tuple with three elements, we are only interested in the float here. We could write it like this. And we say we give that a name, and then we put these placeholder underscores, which is more or less saying I don't care. Which is again important for code. Once you read over this, you see directly I don't need to care about this. If there are names, you're like, where are they going? Where are they used? So this is clearer to just say, don't need this. This underscore placeholder is a feature since C++26. Before that, it was just a normal identifier. And an identifier you can use only once. If you declare it a second time in the same scope, that's not good. If you declare it in another scope, that was always possible, but the compiler would warn you about your shadowing this name. For underscores, there is now a special rule so that these are treated as placeholders, but old code will still continue to compile. You can also use these structurings directly in a range-based for, which I find super useful. Like you have a span of these tuples, so many of them, and you iterate over them. And here we do the iteration with a range-based for, but instead of just saying, well, this one object, we're just taking this one object out of the range and capture it here as this unnamed temporary, and then just give one name to one of the members and then work on that inside the loop. To me, this is super clear because you get rid of all the names that you don't care about. It's very straightforward. This is the only thing my code is doing. Right? The alternative here, well, while this line is shorter, this line is unreadable. You can still think about it and figure out what it is, but in terms of just directly connecting what's going on, it's easier. I mean, of course, I is not a good name here. If you have a good name for what it's doing, this is so much more helpful. At this point, I already wanted to go on Compile Explorer and play a bit with it. I believe structured bindings help code quality by giving better names to the things that you're accessing. So this is one side. You're using things to the structure, but also think about the types that you ever define. How would a user potentially want to destructure your types? So at this point, just create a simple aggregate. So you're creating something that can be destructured, destructure it. Then to that simple aggregate, make it less simple by actually adding member functions, constructors. At what point does it stop working, your destructuring? And then play with the placeholder, play with the range-based for, and then we get back to slides. Or are there any questions? Good. By the way, do you all know the difference between struct and class? There is not really one, except that the first thing you say inside of it is either default public or default private. As soon as you say public colon, they are the same thing. There is in theory a different mangling for struct and class on Microsoft. So there it can make an actual difference if you say struct in one header and class in another, that would not link. And most compilers nowadays warn about if you mismatch class and struct, but in theory they are the same. Um, one more advanced example here with a few gotchas. uh, so that question came up to the structure an array. And if the array is big, I don't want to spell out all the elements. So I want to introduce a pack for saying I don't care about all of these. In this case, from the array, I want to structure the first and the last element. And that's actually possible. I'm naming the first element, I'm naming the last element, and in the middle I'm saying I introduce a pack of placeholders. Now the gotcha here is that C++26, when it introduced this possibility to just introduce a pack on the spot, it had this requirement, it can only be done in a template. If I remove this thing here that does nothing to help me, then it does not compile, because at this point it says, well, structured binding outside of a pack, outside of a template, yeah. And that is, you have to be inside a template. Now, normally I'm always inside a template, so I'll get somewhat surprised. But if you really need to, well, just put a template on it, default it, and then nobody knows, kind of. There is a technical reason in when you implement a compiler why that is important, and it now shows through as a requirement. But it is interesting you can that you can also just in the middle have this pack. And so what we're seeing here on the right is it's doing these two copies from memory uh, from the pointer of the array.
And of course, it cannot be a vector.
Yes, it's yeah, I was just thinking you cannot at all because vector would not implement tuple size. There's no way it could. It needs to be compile time constant. Okay, should we continue or do you want to play a bit more with this feature? This is for you to make it stick to your head, because if I just tell you, then you will forget. I see some people who are continuing, that take that as a sign to give you a few more minutes. But let's give you 3 more minutes and then I continue with the slides. I would continue. We will have more chances to play with code. I want to get to error reporting, something that I asked you already in the histogram example, to do something about the cases when you're outside of the histogram, doesn't fit into any bin, to do something with a function reporting an error. So I want to first take a look at all the big overview here of how we can classify things that can fail. Something that we need to acknowledge is we write bugs. Our software is not always correct. And that's all over the place. C++26 finally acknowledges that this can happen, that people actually write bugs in their code. So I mentioned that with erroneous behavior. It's an erroneous state of when you come into your function and you realize this does not make sense. What I'm currently seeing in terms of input data, that's inconsistent. Something must have gone wrong earlier. Even if it was an alpha particle that flipped a bit, but I don't care. It's inconsistent state. What do I do about this? And that's an erroneous state. Then you have exceptional failure. This is somewhat more expected in terms of this is not necessarily a bug. The coder did the wrong thing, but it's more like this is something that shouldn't have happened, but can in theory happen because of how the system is set up. And then there are expected failures. These are like you do an operation where you know it might not just work. I'll have an example. So erroneous is where you guard against bugs. You have to realize that there will always be bugs. You want to be able to find them. So what you could do is if something wrong comes in, you can just do something that seems useful and continue. But at this point, how do you find your bugs? We had that discussion in the committee when we said we have uninitialized variables, we could just make them 0. And then we wouldn't be able to find the places where we got a 0, where we wanted something else. And just, right? What tool would be able to find that if it is semantically defined to always be a 0 if we don't say anything? So that's where erroneous behavior was added. We had a really long discussion on the mailing lists and everywhere else that we need to fix this, but it would break things in terms of tooling that we currently have to find bugs. You can currently run it with an undefined behavior sanitizer. It would find these places where you have an uninitialized variable and use it. If we define it to be 0, that undefined behavior sanitizer would not flag it as a bug anymore. That's clearly something lost. So this is acknowledging we need to find something in between. And we definitely want that if it's uninitialized, that it's not reading some random things from the stack, because that can be a security issue. So for the security sensitive people in the community that uses C++, it is very important that in the case where erroneous behavior happens, something defined still happens, other than undefined behavior. Important here, same as UB, erroneous behavior is also ill-formed in a constant expression. So you can, if you ever introduce erroneous behavior, find that in tests that run at compile time. So you can also create a test for yourself. There was actually before in older C++ versions, you could not have an uninitialized variable at all. That would already be wrong. Then later versions of the standard then allowed that, but they would require to see that you always initialize it. And that is more or less still the case now. It's now just called erroneous behavior. In user code, this typically looks something like this. You have a function that takes inputs, and not all input values of the given type are actually valid inputs. This is often the case, that you must just use some type that has more possible inputs as you want to support. And so you would document there's a precondition on this function. The condition that you must follow is that in this case it's going to be greater than 0, otherwise it's an error in the program. You can then encode that as an assertion. So that means you run, you check that the condition is true. If not, you abort with the error message, it happened here in this place, and this condition that was wrong. So you are able to find the bug. Just at runtime though, in constant expressions you would also find it, because assertions that run in constant expression also don't compile if they fail. Okay, so that's fine, but what happens if you now compile with assertions turned off? In that case, we're doing the erroneous behavior thing. In that case, we're defining the behavior. Okay, we're just doing something instead of undefined behavior, which is matching the idea that we have for uninitialized variable, that we do want some initialization because uninitialized reads are a security problem. So we don't get unbounded behavior, we get defined behavior. And also note that if assertions are actually turned on, the compiler knows after this line, either x was greater than 0 or the program terminated. So this condition is unconditionally false, and it just can delete the code. So with assertions on, you get this. With assertions off, you get this, but never both. So this is something you can do in the program, and I recommend you write this kind of defensive code. You have assumptions, encode your assumptions in code, potentially in a way that you can turn it on and off if you're afraid of this potentially being visible in performance at a later point, so that you can have a high performance build where all these checks are off. But there have always been reports since many years that running with assertions turned on is in the end a faster executable with rather than assertions off. The reason there is that the compiler sees this is an if statement for a check, this then goes into terminate. The compiler knows, well, the program doesn't need 1,000 ways of terminating. That's not its main purpose. So it realizes, okay, this is the exceptional case. I need to optimize for not terminating. So it will produce assembly code that statically predicts the branch, because in assembly you have this branch of you could go this way or this way. It will statically predict the branch to not terminate. That means your out of order execution in the CPU will happily fill the pipeline with useful work and do all the useful work, and kind of at the side with some idle resources compute the check and say it's fine, continue. And it costs you nothing in execution time. But the compiler has this additional information about x is greater than 0. And so the optimizer has this information here, and so the optimizer can produce better code. And that's the reason why the whole thing can, in the end, run actually faster with assertions turned on. Yeah.
Yeah, wait. Well, it's small. Yeah. Yeah. And okay. Should we also write those if statements?
This part?
Yeah.
Depends on what comes after, right? If you now have, for example, a subscript taking this value, you would get out of bounds on the left-hand side and get into actual UB. And so this would be helpful to actually do something and define the behavior rather than run into actual undefined behavior. If the computation that follows does not run into actual undefined behavior, then maybe you don't need to. But the thing to think about is, do you want this precondition to run into undefined behavior where you never thought about what happens, everything could happen? Or do you want it to run into some defined behavior, which is still wrong because obviously the input was wrong, so you can't do anything really sensible, but you do something that is at least known what it is. It's a design decision and depends on the function.
I have a question. So, should we disable assertions of some kind of law?
Benchmark.
No,
The CMake default is to turn it off, yes.
in all three.
Yes.
But,
Well, in release and release with debug info even.
Release with debug is
well, it's release with debug info, right? So it's just that there's additional data in the binary so that when you go in with GDB, you have more meta information. It's really a question of how you define your build types. When I was using CMake for my VC library, I defined different set of build types because I also had this kind of question. This does not really match the things I want to do. I have very many more scenarios of how I want to build this and what I need to optimize for. So yeah. Again, this is something, in the end, benchmarking is the only thing that will answer this. The theory says assertions can be very efficient and a lot of practice. Okay, next is exceptional failure. This is where you would typically use C++ exceptions. Exceptions have a fairly high cost when you throw. Because they are optimized for the case where the error does not happen. So they are more or less free in terms of if there's never an error, if there's never a throw, it is very, very high performance code. And what is also nice about exceptions, of course, is the stack unwinding. You are not forced as the caller to handle this error information. But you can just say, I'm going to call this. If something happens, the caller of my function needs to handle it or the caller of that function. It just walks down the call stack until it finds a catch statement that catches it. And if it's not caught at all, then the program terminates. And yeah, possibly you want to have a catch-all handler in the end that prints a nice error message for this. Also, there have been recent talks by Khalil about the performance and the impact of having exceptions enabled, because many people said, especially for embedded, we really just need to disable the feature altogether because it's too expensive and it takes too much time, too much space also. And he did work on that and showed that's not necessarily true. Exceptions can be super efficient, both in terms of size, also in terms of being usable on small systems, on embedded. There are really good implementations of this, highly optimized in the Linux compilers. So there has always been this, don't use exceptions. Google is one of those who is in their coding rules very strict about it. Just don't use exceptions, which for them, they cannot change anymore because you should design for the possibility that exceptions happen. If you have a huge code base where you assume it cannot ever happen, then you would have to go through all of this, review what is exception unsafe, and that won't just happen for that. If you have a catch, this is similar to a function call. The catch is then caught when it's unwinding, and it gets this argument to the call, that was constructed when the throw is done. So the throw constructs an object. That object you then get when you catch it. That object can be anything. You can just throw an integer, you can throw a C string, you can throw a std exception, whatever you want. What it is not useful is to throw something that does a lot of work in all kinds of ways. You really just want to communicate some information about the error. But what you want to do here is to just catch by constref. Because it was already constructed when the throw happens, you don't want to copy it necessarily. There must be a good reason to do so. Just take it by constref. So in this specific case, we have the std function, and the std function can be a null pointer if it's not initialized. And in that case, if you call it with a function pointer that just points nowhere, then it would throw this exception of a bad function call. Exceptions are also useful if you ever have an error case in the constructor. How would you communicate an error from a constructor? If you can't have exceptions to handle that, the only thing you can do is have like an is valid state in your class, and then either start by constructing and doing nothing, but is valid is false, and then you have to call an init function. That init function can return whether it worked out or not, or you have this is valid set by the constructor, and then right after construction you have to check, is it actually valid, can I use it? Both of these are workarounds. They can lead to code where you just forgot about doing this. So exceptions are for really just returning errors directly from a constructor the only choice. Now what happens if an exception is thrown and you're unwinding the stack? Every object that is on the stack, now obviously as we're removing function frames from the stack, the lifetime is over. So the objects are destructed, and their destructors are called. And this is really important, and a very, very important feature of C++, that you have these destructors. Because there's, what do you always want to do if you have any kind of resource? The obvious thing is to have memory on the heap, but it could also be a file that is open or a connection to the network or something. If you have any kind of these resources, these should be connected to the lifetime of such an object. And then you construct that at initialization, and you destruct it in the destructor. You free all the resources. This is called the RAII pattern in C++, which is a stupid name, but it's stuck. Resource acquisition is initialization, whatever that means. So you construct the resource, you free it in the destructor. Once you have that, you're mostly exception safe, because every resource is then freed when you unwind the stack. Sometimes you have interesting situations like std vector. Consider std vector, you do a pushback. Now it needs to reallocate because it didn't have enough memory. It reallocates, now it has to move all the elements. It starts doing that, the move is actually not working, it has to do copies. Okay, so it starts copying over. After it copied 10 of them over, one of them throws an exception in the copy constructor. What do? You're halfway through. And this is why it actually copied, because then it can say, well, I still have the old ones. Consider it was moving. It's moved 10 of them over. And then a move constructor throws. Oops. Can I move them back without it throwing? Which would start moving back after 5 of them a move constructor throws. You're completely lost. Okay, to make that exception safe, we got that feature of no except. And we got the default of move constructors should or must be no except. And this is what std vector then checks for. Is the move constructor no except? If yes, then I can actually move them on reallocation. If it's not no except, then I will copy, because otherwise I can land in the state where, well, we can only terminate the program at this point. Okay, and so that leads us to the no except keyword. This is where it came from. This is where it was used as an optimization for SID vector. It is really most important on move constructors that these are no except, and all the other ones, yeah. There's a reason now in senders and receivers in C++26 where no except also has the additional meaning, but I'm not an expert on that. Before I go on from exceptions, any questions on exceptions? Yeah.
The catch part of the code, can we throw another exception?
Yes. So you can, from here, because at that point the exception is already caught, you're not unwinding anymore. So from here you can throw another exception, or you can rethrow the same exception by just saying throw. So you can inspect, I see that this happened, but I don't know how to handle it, and so you just rethrow.
So what's your go-to way of like thinking of these edge cases of what to catch or what could break the code? Like how do you approach this?
Do you mean when to use exceptions? When is an error exceptional?
Exactly. Like, yeah.
Yeah. Maybe let me go on to the last one that gives examples for the ones that are not exceptional. But in general, I would say a condition where you say, okay, my system is in a state that was not expected. It was certainly possible, but this is more or less a problem that cannot be solved from anywhere here. So you sometimes have interfaces that from the call side decide whether you want exceptions or a different mode of failure, because sometimes it's only the caller that can decide whether this is truly strange that this error happened or whether this is more or less common that this error happened. So it's not always obvious, and sometimes it's for a library not possible to even decide. It just, I guess, takes some practice and experience, but I'll continue. Okay, the next one I want to show here is still optional. And a case where this would typically happen if you do some kind of lookup in a map or so. Right? You have possible keys and then values attached to these keys, and now you're asking, can you look up the value to this key, please? And then the lookup can say, well, no, I did not find any. It's kind of expected that this can happen. So this interface does communicate this, yeah, you can get a string, but not always, because it's optional that you get the string back. In the case where the key doesn't exist, what do you get? The optional is more or less just the state of all possible strings plus one more state. So optional takes a type and adds one more possible state. It's kind of like a pointer that was often used as an optional in terms of if it's a null pointer, then the thing just was not returned. Otherwise, it points to the thing you actually wanted to have. So here we would call the lookup function the return value we can directly evaluate in the if statement. So we can do this as one step, and then it's also scoped like this. And if the value is true, because an optional is convertible to bool, or it's rather Boolean testable, bit of technicality there with the explicit keyword, then we got a value, and then we can dereference the value, or you can call the value function to call the value. There's a slight difference in dereference and calling the value member. The value member would throw if you're doing it wrong. So if you actually got an optional that is false and then call value, this one throws. This one is QB if you do it. And also the conversion to bool, there's this equivalent one that has value function that you can call on it. Right, and so this would be the typical case where you would expect that this can happen. You call it always with a branch where you can handle both cases. Whereas often with something that is an exception, you would just call it and now have no error handling code, or potentially just to try around a big block of code and then a catch for a lot of things that could potentially happen. And you might have a complete subsystem of your application that is in a try-catch block, and the whole subsystem somewhere deep inside fails with an exceptional error. And what you decide is, well, let me just delete the whole subsystem, reinitialize it, and start again. This is very different to that. This is something that is expected. Okay, I don't have a key. Let me insert it or whatever. Right? It's something you want to handle directly.
Can I make a comment?
Yes.
Because sometimes I see people confused by the operator, the reference there. So value is not a pointer. It's not even a smart pointer. It's just a syntactic trick to return the value.
Yes.
So it could be another function like value, but so.
Yes. Except for what we added in C++26, we now have optional of references, which is internally stored as a pointer, and the false case is actually stored as a null pointer. So optional ref is an optimization in terms of the storage, because for what we're doing here, we need to store a bool and a string. And for the, if you had like an optional std string ref, you would have just one pointer that has this. Right. Very similar to the optional is the expected. But rather than having just this Boolean information of this, I gave you the value, I did not, it tells you, I gave you the value or I gave you an error value. It's more or less a variant of, it can be only this type or this type, but with this additional semantics of this is the value that you actually wanted to have, or this is the error case. From the interface, it is more or less the same that you have, like I'm saying here, that you have this the reference, you have the value member, you have the testable for Boolean, you have the has value function, but there's now also an error member function which returns you the error value of the type E. So like this optional T, the T is the thing you actually wanted to have, and then we have any kind of type that you can put here for an error value. Now, what you could do here is we parse a string, and if that fails, for whatever reason, the string was malformed, you can report it failed, and it failed for that reason. Not just it failed for a certain reason. And that's where this is mostly useful for. And then the old way of doing this, you would have a parse function that always returns the error code and then has an out parameter for the value. And so you would have to create the value object beforehand, then call it with a reference to that object that you created, and then you need to check the return value. Is it an error case or is it not? And if not, then you can actually read through the pointer and find the new value. This is old style. Don't do this in new code, I would say. And if you can refactor old code to use optional or expected instead of this pattern, this is better. In general, just avoid out parameters. Whichever way, whether that's via reference or via pointer, out parameters is not a nice way of looking at functions, also for the optimizer. There's this concept of a pure function. A pure function takes inputs, does not look at global variables, and then provides outputs through the return. This one goes through a pointer somewhere else and stores through there. This is not this kind of nice function that you could easily just reason about. Okay. So the first thing is acknowledge that code has bugs. Even if your code is bug-free, you will be called by people who write bugs in their code when calling yours. So you need to make sure that they don't come and blame your code isn't working. You want your code to directly flag the misusage of your code. And that's why you should code defensively, have these assertions in there. Encode all your assumptions about preconditions or whatever in code. Static assert, assert. You don't have to necessarily use the assert macro that's in the C assert header. There are other ways of doing this. There are many nice and useful ways of doing this. Then use exceptions for exceptional errors. Like I mentioned, the whole subsystem needs to be a reinitialized kind of thing where this could help. Also care about, even if you don't use exceptions, about exception safety. Just think about if it were to throw anywhere here. I'm calling a function. This function, if it throws, what happens? Does it clean up correctly, or do I have any resource leaks? And then for any operations that can sometimes fail, use optional or expected, depending on what is more useful here. We have 10 minutes to break. I would say get started on playing a bit with these. Try to invoke actual erroneous behavior. So GCC 16 implements this part of C++26. The only language erroneous behavior that exists is to create a variable that is not initialized and then use that variable, read from it, like it showed the x plus 1. Check what the compiler tells you about it, both in runtime code and in constant expressions. And then, yeah, write a function where you would have a comment, this function has a precondition, and then implement defensive code. Play a bit with exceptions, catching, and also optional expected. Any more questions? Yes.
Can you maybe clarify a little bit more where does it make more sense to grow instead of why not just always use expected? Does it make it explicit for the function signature?
Yeah, you're basically saying it. If it's helpful to the caller that it's very explicit that this thing can fail, right? Then if you return expected or optional is the way to do that. If it just throws an exception and then it's not part of the signature other than whether there's a no except or not at the end. The exception is more of an I'm not getting in your way kind of function, right? You would just go and program as if nothing could ever go wrong. And then the exception, yeah, at some point happens and you handle it somewhere. I would say some of the older C++ code that was trying to do error handling was using too much of exceptions, where they should have done something like optional expected. It wasn't there, so they would have to use error codes. They hated it so much that they used exceptions instead. And so just looking at older code is not always instructive in that sense, which one you should use. I think you need to make up your own experience there and just try.
I can make a comment, an
Yeah.
example. For example, if you are parsing an initialization, a configuration file, you are parsing and it's deep in the data structure, I don't know, JSON or whatever. You don't want to every single step to check. I mean, you expect the syntax is correct, but you don't want to check every time. So if at some point down in the tree of calls to the final parameter there is something wrong, you throw an exception and you catch it at where you ask to parse the file. You don't want to do micromanagement of errors during the parsing. And I have a comment on where to use there are two places in C++ where you are obliged in practice to use exceptions. One is in constructors, If you want a constructor to fail, there is no other way to make it fail. And the second is when you have operators, because they have a fixed syntax. So if you have operator plus, you don't have a Boolean that you can or return code on unexpected or an additional parameter. The only way to fail there, if you have to fail, is to use an exception. So that's...
Yeah, most of the times in my experience, if an operator fails, it's more of an erroneous case. But yes, you're right. And as you mentioned the constructors again, I had to think of destructors. If you throw in destructors, you're getting in interesting problems on stack unwinding, right? If something throws and you're unwinding the stack and now your destructor also throws, you have two exceptions in this point. That just means terminate. You're done. This is why the default for destructors is that they are no except. If you really want to throw from a destructor, and there are a few use cases, especially in unit testing, where that can be useful, you have to write your destructor and then say no except false. That's the only way to make it actually work, that you can throw from a destructor, because the default is that it cannot. So if you throw from a function that is declared no except, and that exception wants to get out, that is an immediate std terminate. So by the way, we're in break time until 11. Feel free to take your break as you want. Okay, break is over. Is this on? This is, I don't hear a thing. Let me turn this higher. Can you hear me now? Yeah, it's on. Okay. So I turned up the volume.
Yes, I lowered the volume,
But is it?
it was
I muted myself anyway. So there
now it
is.
works.
It seems to work. But do you hear me through the speakers? Okay. It's just. Yeah, I can hear it. I can also speak directly into it. Or just touching. Anyway, okay. Do you want to have a bit more time to play with these error things on Compiler Explorer, or should we just rather continue? Personally, I would continue. Okay. On benchmarking, I think I'm going to skip this one. You will have extra lessons on the topic and related things. Not this one. So you can go through the slides if you need to. There's also lots of information in the exercises on benchmarking. I will do a very quick overview on ranges, not much. And then I would go into showing some of SIMD, some of the work that I put into C++26. And if we have enough time to also do the peak flop benchmark here, and you can see, and we hopefully get through that quickly. So we have a bit of touching the code together. Okay, on ranges, also not much, just going through this so that you have an idea what it is. A range is defined as something fairly simple. Anything where it can call the begin and end on that thing, and where this begin iterator, when you advance it, actually reaches the end iterator. That's a range. In terms of the concept that exists, there's a STD range concept. It's only the first bullet that is tested, because the second bullet you can't test just from looking at the type. So this is undefined behavior if that's not true, which kind of makes sense. Once you start iterating a range and you start advancing the begin iterator, it never reaches end, or it has to at least go out of bounds to reach somewhere. That's obviously undefined behavior. That's also something I did not mention about concepts. Concepts in the standard, also in the way you think about it abstract, they have two parts. One part is the one that is testable in code. And then there is another part that is just semantics that you can only describe in words. Both of them often need to be true. This one part is just not testable. If it's not true, it's undefined behavior for most parts. It could also be erroneous behavior, depending on how it's implemented. It's typically just a library function that has this kind of precondition. Okay, some examples for ranges is obviously a STD vector, but also a STD span, which is a view into something which is stored else. We have the C array, we have a STD array that we pipe through a range adapter, and we'll show these in a bit. So this thing, this whole expression is still a range. So C++20 added this concept of ranges and the views and the range adapters. The idea here is to have something that is lazily applied. Before that, you would only have this kind of STD algorithms so that you could take a range and just modify on the range or write into a new range with each modification. But writing that as one algorithm after the other, that would be super inefficient, because you go over the whole memory and again, and we're bound by memory most of the time. So that will be super inefficient. The range adapters do this differently. You create, in this case, even data on the fly, but you can also just adapt that. And none of this is actually happening until you iterate over this. So just writing in this case, views iota, views filter, views transform, that whole expression does nothing at runtime until you start iterating over this. And yet every time you dereference, you compute. So we're moving from memory access to compute, which is the thing you should do all the time. Every time you access memory, do as much as it with you can before you go to the next part. That's a very important thing in terms of optimizing for modern hardware, where modern is more than 20 years old by now. Back in the 70s and the 80s, you would just go over memory and do things. That was the way to do it. But since we have caches in the CPUs, that started with a 386 or 486. I think it's a 486. That's long ago, right? And so sometimes even you compute more than necessary. You recompute things you already computed just to have fewer memory accesses. Because most of the time our CPUs are just waiting, idling, waiting for data to arrive. Okay, so range adapters are one part of the story that makes this easier. Just to look at one of them so that you get an idea. And to warn you, if you ever look at CPP reference for these range adapters, they look horrible on CPP reference. It's just a wall of code that you get to see and you don't get to see the simple thing. It's actually pretty simple. So I would recommend you, once you understand what I'm showing for the drop view, look at CPP reference for drop view and try to see in this wall of code and text where the simple things that it actually is are hidden, so that if you look at another one, you know where to look. So what we're doing here, we're creating an initializer list. This is now actually auto is going to be deduced as a std initializer list. And we're saying, okay, we have a number. Well, this n is the wrong way around anyway. So there's a number of values that we want to drop that we're passing in here. So if you were to compile that, what you see is that we're dropping from the start of the range that many elements as are in this value. It's a pretty simple thing. So this doesn't actually even compute on the data itself. It just computes on the iterators, that once you do this advance by one, it would just advance further. And there are two ways to write this. There is a ranges drop view where you give the number, where you give the range that you want to act on and then the number to drop. Or you use this pipe operator, which is in principle just the bitwise OR, but we're turning it into a different meaning like we did with IO streams. So you pipe your existing range through this view, and you can also write this. This is actually, I think, wrong. This should be std views drop. So a drop view in ranges is a drop in views. And there it has a different signature because this is now passed in through that pipe operator, which is somewhat special, and now you only get to pass all the following arguments. And you will get to see both of these in CPP reference. Okay, then this is also a range. This is not std ranges, but it's still a range. And it's a view. Std span is a view on data. So it's non-owning. And this is also true for any of these range adapters. These are non-owning. Once you create them, if you copy them around, you're not copying around data. You might be doing dangerous things. It is often safer to just construct them on the fly and not pass them around too much. If you want to see the edge cases that are hard look for Nico Yusuitis. He has strong words for some parts of ranges where you can get surprising results, especially for the filter view. Okay, Stutzspan also is a view. So if you copy this around, the thing it references still needs to be alive. Right? That's the idea of a view. One thing that we always had in C and then later in C++ is this concept of a pointer and a size. We're pointing somewhere in memory and then say there are so many elements that are valid that you can work with starting from that pointer, and then you can increment the pointer. That's what the Stutzspan basically now represents in a nicer and more useful interface. So it always represents contiguous ranges because it's this pointer and size. So you're going from the pointer in memory contiguously. It makes it somewhat safer to access. It's still not necessarily always checked, but if you turn on fhardened, the compiler flag, many of these operations in Stutzspan will then be checked at runtime that they are never going out of bounds. Sometimes you have functions that can take any range. So you would be able to say, I do a template, and whatever kind of range comes in here, I'm going to be able to work with this. We talked about template bloat before, that if you have such a template, you could instantiate that with many different types, and so get many different copies of that function. If that function is large, that's a lot of code that will be in your object file. Stutzspan is a possible way out because you can say this function just simply takes any kind of contiguous range, so let me just use a Stutzspan instead. So every possible range, different types, all then fold down into this single thing, the Stutzspan. And so you only have this one function, potentially this span t, so the t is still different. It could be a float, it could be a double, but it's not different containers and different range adapters and whatever it could be. Range adapters typically don't go into span anyway because they are not contiguous. But anyway, this can be helpful sometimes to just use a span instead. Where you typically use it is on function boundaries. So the function argument takes the span, and here's my recommendation, just take it by value. The span is a pointer and a size, and as I mentioned on Linux, at least this will be passed in registers. This is going to be most efficient to just always pass by value. And the two things you want to know here is that the template argument can also be const t. So the span that you cannot modify the data is not const span t. The const span t is just the one where you cannot change the pointer in size. You need to make the data that it points to const, and the data that it points to is of the type that's inside the template argument here, and so that needs to be const t right there. Also, the span has a second argument which is defaulted to dynamic. So at runtime, at compile time, you don't know what size it is, but you can also actually put a certain fixed size there, then it's a statically sized range. Statically sized ranges are super important and helpful once you start getting working with SIMD. There's a good match there for high performance when you know all of these things at compile time. Okay, we've seen that before. You can just go range base 4 over it or any kind of other range operations. Then in addition to the span, we also got the MD span. MD is short for multidimensional. That was added in 23. It generalizes this concept of a view onto existing data, which is in span just one-dimensional linear, into multidimensional view. You still have a single dimension of data, like in a state vector, you would have your data, and then you put the MD span on top as a view onto that linear range of data. And now it has an index mapping of a multidimensional index space onto a one-dimensional index space into this actual storage. MDSpan is super flexible. It supports arbitrary layouts and strides. It also has different accessors, so you can do crazy things like access memory that's actually on the GPU or on a different node, which is where all this design is coming from. That is not necessarily part of the standard library implementations, but you can provide your own accessors and plug them in. So this is a huge toolbox, but just to get started with the basics is already interesting here, just to get actual multidimensional access to data. Because the only way otherwise we could define multidimensional data were C arrays where you pass multiple constant sizes for the extents, which is not really that usable and also somewhat surprising sometimes where in memory you're going, and this is very well defined. So here is a simple example. We're creating the storage backend as a std array, and now we're creating a 2D matrix and a 3D matrix with the different sizes and the extents. And this is just using the defaults of how this is mapping. Not going to go into much detail. If we have time, I might show an implementation of matrix multiplication using MDSpan, but we'll have to see about time there. Also, we added a multidimensional subscript operator. Up to SIP was 17, you were not able to do that. Well, you were, but it was more or less ignored. Then it was deprecated that you could do this stupid ignored feature. And then we added the actual feature that you can really now overload it for multiple arguments. And so that is something that MDSpan uses, but you can also use it yourself to have multidimensional access in this fairly nice syntax of subscripting in these multiple dimensions. Okay, span is fairly simple, MDSpan is not. You can do all kinds of things. Super interesting ways of going through memory just for cache efficiency. If you get into this part of the lecture where you learn about memory architecture, you will see why it is so important to think about how you move through a big part of memory, in what order you go through. Because if you repeatedly go through the same things, you need to understand how it is stored in caches and how you can keep the caches hot to reduce the actual memory transfer from the RAM into the caches. Transfer inside the caches is cheaper, but yeah. Also, we have linalg in C++26, so there are some functions not implemented anywhere in the standard libraries, but this is the basis. You need to have these multidimensional things first before you can then have operations on them. Okay, on this section, you understand now what a range is in terms of the concept. You have this idea of a range adapter that allows you to give a different view onto an existing range without actually computing anything until you access the data. You have span, you have seen it before. You now know that it is important, if you want it read only, that it's part of the template argument here. And MDSpan, if you want to get into this, it'll take a bit more work and time. Let's take 10 minutes. That you can at least create a simple array, pipe it through a range adapter like a drop or something else, and look what's coming out of this. Also, what I did not mention in the slides before, but this is also interesting, the end of your pipe can be a std ranges to, and then in the template argument, you give it a container title, like a std vector. And then it will create that std vector from whatever it created through the whole iteration, and the whole expression then is a std vector, so you can say just auto new container equals that whole expression, which in the end creates that final object. Sadly, it does not work with arrays at this point, which are fixed size. I hope we're getting there in the committee, but I think it will not be available in 26 implementations anytime soon. So it also does not work with SIMDs, but maybe at some point. Any questions? Otherwise, at past, I would continue looking at SIMD.
I have a question. Do you have to specify in ranges 2 SED vector or SED vector? And so...
Yeah, you know the discussion?
No, well, I know that there has been discussion, but I don't know the answer. So it was a genuine question.
So the feature was introduced that you could just say std vector and you would know the element type and do the right thing with CTAD. All the compilers and standard libraries implemented it like this. And then somebody said, well, but the language specification doesn't allow it.
Yes,
and so there was a core issue that got resolved, and it got resolved in a way that was wrong. So everything that was implemented in all the compilers is now wrong. And you can still specify, it still works. You can still say std vector without specifying the template, but it's non-conforming according to the standard. So if you want to be sure that it compiles and continue in the future, you probably need to specify the template arguments, and it's got to be a type, not just a template.
But the fix will be to allow the template there, or?
So the fix is for the T that is an actual type. So it's got to be a specialization of vector. So you would have to say std vector int.
But even in the future, or?
Oh, you don't know what's going to happen. The current state of the standard is that, yeah. I wanted to show one more language feature that many people don't know about, that it exists in C++ and it is fairly old. It's namespace aliases. So you can shorten your namespaces, like std ranges, the sub namespace, and I always do it for my SIMD sub namespace as well. You make this namespace ranges equals std ranges. You probably know that from many other languages. Python does it all the time. You have long namespaces. You always shorten it in your source files. You can do that in C++ as well. So you could just drop the std on all the ranges and just say it's like that. This is especially interesting if you have an implementation of something that's coming up somewhere in the C++ standard. It is implemented in the third-party library and it's in a different namespace than std, as it should be. But it's in potentially a subnamespace. And so you could have a namespace alias just for that third-party library. And later, when you are able to switch to actually the standard library implementation, you only have to switch the namespace alias, and that's it. It might be both, yes.
So that's why, because in the slides at some point it's commented.
Yes. It might just be an alias for ranges views. Yeah. Okay, I hope you all had a chance to get something done, even if not all. We have 1 hour left, and our afternoon is half an hour shorter than the previous 2 days because of the seminar in the afternoon. So I would just want to continue. This slide deck ends here. There were a few things that I would have also still wanted to talk about. We didn't get to that. Just a quick mention. Conversions, type punning. We talked a bit about conversions. You have the static cast that you probably know about. You can just often implicitly cast. I mentioned the const cast. I did not mention the reinterpret cast yet. Reinterpret cast is something that people like to do, and it's most of the time undefined behavior to do so. It falls under this concept of type punning because you have one type, you interpret it as a different type. There are specific rules when that is okay. If you don't know these rules, it's not okay. Just assume it's not okay. So reinterpret cast should be a red flag. Instead, almost every time you can use a std bitcast, and that will do what you want. Std bitcast works on a value level. So instead of saying the thing that already exists in memory, I reinterpret as something else, you say the thing that exists in memory, just blast the bits into a new object, and now it has a different type. And that is so much safer because now in terms of the abstract object model of the lifetimes and everything, you have a new thing that is the other type, and that just works. So you can take your float and stit bitcast it into an unsigned, and that's okay. If you take your float and reinterpret cast that into an unsigned ref, that's undefined behavior once you access it. Okay, so just remember, reinterpret cast is bad, stit bitcast is the way to do it. If you want to have a big range reinterpret casted, just iterate over it in the thing that it is originally. I think somebody needs to open the door. The thing that it is, and then element by element just bitcast it, rather than reinterpret casting the whole thing. Name lookup, ADL, operator overloading. So name lookup is an interesting topic and something that I, at least, when I started with C++, I was just, okay, why does this not find my function? And I was just moving things around until it did, and I did not understand why it worked and why it did not work. Name lookup is somewhat involved. Just consider that you should get a bit of an idea also potentially of ADL. The simplest thing is just to fully qualify your calls. Just put the complete namespace in front of it and then you know what you're calling. Sometimes you cannot, like for operator overloads. Operator overloads will always just be implicit calls to just some operator. And in that case, you depend on ADL, which is argument dependent lookup. So it looks at the types of your arguments, and from that type, it infers where to look, in what namespace it needs to look for the possible operators. It does not look everywhere. It just does not take an unrelated namespace, which makes sense. But which namespace are the related ones? That's the big question. The simplest thing here is make all your operators hidden friends of the class. Look up what hidden friends are. I will probably come around to show you in code, but hidden friends is the solution to most of your problems, except if you cannot implement it in line. I wanted to get a bit into the design of data structures. This has to do a lot with memory access again, so maybe you will learn a bit about the idea there when you talk about memory. Debugging C++, well, you have to figure that out. Numbers is potentially interesting. There is a very simple header there. You get pi and some other constants that you care about in float, double, and long double precision in a fairly simple way. Just if you include numbers, then it's instead numbers pi, pi underscore v, and then the type that you care about. So that is interesting. It's small, but nice. Okay, and now I'm going to switch over to a different slide deck. So in case you wonder how I create my slides, all the previous slides were done in MARP. That's Markdown based. This is now LaTeX Beamer, which I have been using before all the time. And I just went over some slides that are coming out of my CPPCon talk that I gave on SIMD. I updated it for what has changed since then. And made it much shorter. It still will take a bit of time. This is one of our meeting locations and committee meetings. Most of the time, I get to see this like for lunch break, and the rest of the time I'm sitting inside a hotel without any windows. So this is especially worse if we go to these places. Okay, so I want to talk about SIMD, and you will again see that when you talk about computer architecture. Just a very short idea here. SIMD idea is that you do multiple operations in one instruction. So normally you would do an operation and then in time the operations come one after another. With SIMD you just fold that and you do multiple operations, and so you can do a lot more over time. So one instruction just does more work, same work in less time. But there's another interesting feature, and that's instruction level parallelism. Because CPUs can do multiple instructions in one CPU cycle. So you can do the same work in even less time because we're folding another part down here. So we have a SIMD vector and then a second SIMD vector, and we're doing that at the same time. This is how it more or less developed, and we're kind of stable now on 86 curve. We have a 16x speed up on the AVX 512 CPUs in terms of using SIMD. This is also using fused multiply add instructions, which is why this is going up, the scalar case. And both of them are using all of the ILP in terms of how I've plotted this. So you see the number of floating point operations per clock cycle in single precision float. And this is kind of the speed up you're missing out in single precision float if you don't use SIMD. So the first thing I want to say here, even though it's called SIMD, I also like to call it data parallel types because it expresses data parallelism in your problem. And that can map to both SIMD and instruction level parallelism. If you ever wondered about unrolling a loop just to get more parallelism, this is also what it does. I gave you that task of reaching peak flop. We're going to do this on the slides here and then potentially again in code. The problem often that we have, what we give the compiler is sequential scalar code. We have lots of data, we have that range, we're going to take a for loop to iterate over the whole range, and then we take one value and work with that one value. That's kind of wrong. Every time we know we have our measurements, I need to do the same thing. I only use a for loop because that's what the language gives me to tell it needs to do it on all of them. I did not necessarily meant to say you have to do it in that order. You can do it at the same time. But that's not what the language encodes. So we input sequential scalar code, and the compiler output often then is no SIMD, little to no instruction level parallelism. And you can see that in the peak flop benchmark that you hopefully got started on yesterday. So you have this multiply add, which the compiler can translate into a fused multiply add instruction. So there's one instruction here. And as we see, this modifies X. It reads X and modifies X. So what happens is that it has to wait for the fused multiply add to produce a result before it can then execute the next instruction. These fake modify, fake read, you did that potentially with a benchmark do not optimize. We're introducing just to the compiler that it doesn't delete our code because the code, what we're doing is useless. And if a compiler sees useless codes, like I mentioned, it throws it away. Okay, so if we just compile it like this, and I used O3 here just to make everyone happy, I'm actually using all the potential vectorization because O3 adds some more vectorization passes. Yeah, we get a quarter of a floating point operation per clock cycle. Okay, now add march native, and we get fused multiply add. So without this, it assumes it does not have fused multiply add instructions. They were added later into x86. So you need that, and then this turns rather from 2 instructions to 1 instruction, then you get actually a factor 2 already from that. Now I'm using SIMDVec instead of float. So I just replace a type. And the simple replacement is just to use the SIMDVec without specifying the number of elements. Then I already get some speed up. But by specifying a multiple of 8, so I'm basically saying take the default size of one SIMD register, number of elements, and then multiply by 8. That number 8, something you might learn about. I can also try to explain. So it's a fairly big thing. It's the number 8 is the instruction level parallelism. Once I do that, I get to 8 flop per cycle without march native and 64 floating point operations per clock cycle with march native. That's from the worst case to the best case. That's a factor of 256. That's the kind of parallelism that's on the single core. It hurts if you realize how much there is and how much we often just don't use. So if you look at simple, it's not simple. If you look at perfstat, for example, and perfstat tells you you have that many instructions per cycle, and it's 4 instructions per cycle. Well, yeah, that sounds like best, right? I have all the instructions that I could possibly get through this thing, but is it actually effective? You can still not tell. In this case, you would see it's not a good instruction per cycle because you issue that instruction and then it takes 4 clock cycles until we get to the next. So it is mostly idling. In this case, if you run per stat on it, you would see the CPU is just waiting all the time. It's like, and in this case, if you leave out the 8, it's more or less the same. It's a factor 8 less. Because it would, again, just do the whole thing as one SIMD instruction and then have to wait for 4 cycles before it can do the next. So that explains at least a factor 4, because every cycle I can add another one. And so the number 2, so that is the final 8, comes from the fact that actually the CPU cannot just execute one FMA instruction per clock cycle, it can issue 2. Every clock cycle you can do 2 FMAs, and an FMA is 2 floating point operations because it's multiply and add. So it's 4 floating point operations per clock cycle that you can issue. And not operations, but instructions. And since these are AVX 512, it is 16 floating point elements in there. So it's 4 times 16, that's why you get up to 64. Any questions on that? Lots.
I didn't get, you said that on the left, per instruction, we have to wait 3 clock cycles before we can execute the next instruction.
Yeah, so every instruction has a latency and a throughput. The latency is the time it takes from starting the instruction until you have a result. And the way that loop is built, you write into X and then read in the next iteration from that X. So you need to wait the complete latency of the instruction before you can execute the next instruction. That's why it takes 4 cycles for every iteration. And there are basically 7 more FMA instructions that you could at the same time execute.
And the second question I have, those CPU clock cycles that we are waiting, if the machine is saturated doing something else, could those cycles be used by some other process or some other?
No. So this is a single thread executing on a core. So with hyperthreading, that is super fine-grained on the clock cycle level. You could potentially do something like that, that you can say, in this one clock cycle, I'm issuing this, then I have 3 clock cycles where some other hyperthread can work on this core, and then I go back. But I haven't seen that high, like going back and forth between hyperthreads. Most would recommend to just disable hyperthreads altogether, and in that case, no, there's nothing you can do. If the Linux kernel would like to schedule another process to make use of these 3 cycles, that's never going to happen because the context switch is just so much more expensive.
Thank you.
More questions, or was it answered?
So this is probably very silly, but for example, with the march native, is there anything fundamental that prevents the compiler to just do this by itself, or like why do you have to be explicit?
Because, well, of course, the compiler could change its defaults. But once you change defaults, people's code will break. Because people did just start relying on defaults because they did not consider that it could change and that could be a problem for them. So native can lead to situations where currently you compile code and then distribute the binary and it needs to run somewhere else. If you just change the default to be native, that will break because it can then happen that you ship your binary to a system where that is incompatible. Yes, we suffer from wrong defaults everywhere in the C++ ecosystem. Just be explicit about most of the things.
But what I mean is, so for example, you are explicit about the M-arch native, but then as you see, for example, it did by default like the 0.5 flops per cycle instead of the 64. Like, why isn't it able to
Okay.
do the seemed like by
So these two sides are very different in what they're actually doing. This one is computing one sequence for one value. This one is way more. So SIMD-VEC float size is 16. Take that by 8. We're up at 128 values that we process in parallel, and these are different values. So this is not always something that is applicable. If you only have one input, you can only work with one sequence. But if you have a lot of inputs because you got a big range of measurements, then you can say, I'm going to take 128 measurements at the same time and process them in parallel. And only then can you actually apply this and do something like it, which is kind of what I'm getting at with the next slides.
Yeah, answered already. Okay.
Okay. And that's part of the message here, right? The left-hand side, the naive benchmark was slow, not necessarily because it was stupid. It did not contain parallelism. There was just no parallelism that the compiler could turn into running in parallel, because it is only one value. There is nothing to parallelize.
Sorry, I wanted maybe for you to come again on the fact that how does like widening up the data structure, so the CMD-VEC in this case, then make the compiler understand that it can schedule more operations in the same clock cycle. So I mean, for me, this is a bit like awkward to think about. Like, I widen the data structure, so how does it make it do more?
You can also do it here. Instead of having a single float variable, you have many float variables. And then instead of having this one statement here, you have it for all of these variables. And that adds parallelism to this function. And then the compiler can translate that also into the parallelism that the CPU can make use of. It's just that if you do it like that, you have a lot of things to write. You could write it as a std array and then again iterate internally over that std array. This is just very explicit about expressing that parallelism. You're saying, I'm creating this one thing with many things in it. My intent is that you do these at the same time. It's about expressing data parallelism that you would implicitly specify if you do it with separate floats.
Okay, thanks.
Okay, let me do here.
So just a curiosity, what will happen if you try to run this code on a very old CPU that has no SIMD instruction? It will just fall back to the sequential one, or something else?
So the idea of the SIMD-VEC float without saying anything is that you would get the best performance in terms of SIMD on the target system. So if you actually have a target where there are no SIMD instructions, that means it's one element. And the ×8 here is certainly something that you need to figure out from the CPU documentation. And so that is target dependent, and it's not a generally good idea to just put like this and hard code it in your code. If you want this kind of instruction level parallelism tuning factor, I would recommend to have it somewhere as a tuning factor outside algorithm, where you can actually then tune it for the different targets.
And then just going back to the previous question about the compiler doing turning everything into SIMD, could not be possible to add maybe an additional optimization step, maybe to be enabled with a new flag in the compiler that tries to just turn every possible thing which is safe to do in SIMD instruction? Because there are other languages, I think, at least Julia that, okay, it's not even a full compiled language that tries to do it.
I mean, yeah, C++ compilers also try to do everything they can within the rules of the language standard to do so. Auto-vectorizers is exactly trying to do all of this, and it's part of O2. You don't need O3 for auto-vectorization nowadays. It was different, but many of the auto-vectorization stuff became so ubiquitous that it moved into O2. And so that's what I meant. If you have many float operations here, the compiler would see that it can then pack these into actual SIMD registers and do SIMD operations on them. You would get this vectorization here. And it's not necessary to use SIMD vector.
So why in this case it was not vectorized?
Because there's only one value, because there's only one float.
Ah, okay.
And
okay.
I need to get to the next slide for you to see a bit of the point of this. Yeah, but maybe just to answer this before it comes back again, it's part of interfaces. Just think of a CMath function. It takes one float, and then there's a function call there, and that function has no way of taking more than that because the function is just on an ABI boundary. It has one value. It now does actually, in implementations for some of the functions, do something very similar to what we're seeing here. And where can it take the parallelism from? It's nowhere. It has one X that came in. And so what the compiler does here, it tries to auto-vectorize also CMath functions, which only happens if you turn on fast math on the compiler, because then it can reason much better about what floating point can do and cannot do. And also for all the math functions, you have this stupid variable called erno, which is a global variable that it has to set whenever some floating point error cases happen. If you have multiple of these happen at the same time, that would just be wrong. So erno leads to basically inhibiting all kinds of vectorization. So if you turn on fast math, magic happens in the math header where there's an if-def float fast math, then declare my math function with a special SIMD attribute, which the compiler, which is a compiler extension, and which points to a different implementation of the function. The different implementation is then, it's in libmvec, whereas all the CMath functions are otherwise in libm. libmvec then has a special vectorized implementation of the CMath stuff, and so it would directly dispatch into vectorized optimizations of it, and so it could work. But this is very special, and you won't do this in your code. And you will implement something that is mathy, that takes one value and you do something with the one value, but you lose all your parallelism just because you use that kind of interface. These SIMD attributes, and just look at it, math header if you dare. It's took me quite some time to decode how it works and to find the implementation in glibc. The library boundaries often inhibit parallelization, and so it's a bit of a question whether the interface should not just be that. Because here you're saying, yeah, I can do parallelism, and I can scale my parallelism depending on whatever is the actual problem. I can give one value into it, I can give a lot of value into it, and that provides parallelism to the implementation so that you can get to what the right-hand side is able to do just because the left-hand side just hasn't enough data to be able to do it. Even though if the compiler in this case clearly could auto-vectorize it also. Okay, more questions left?
I just wanted to clarify about the multiply by 8. So what I think you already said this, like this is architecture dependent, but so here we multiply by 8 because we assume the register is 64 bits and the float is...
No, the 8 comes from instruction throughput and latency. So how many instructions can the CPU issue in one clock cycle, and how many clock cycles does it take until you have the result? So you can issue 2, and it takes 4 clock cycles. So these 2 dimensions makes it 8 before you can then issue on the dependency chain the next.
Oh, so even if it was double, we could have multiplied by 8.
Yes, I think double has the same, yes. It's just the SIMD vector size is half of it. But the 8 stays the same because the latency and throughput numbers are the same for double precision.
I see. So it's not like, since it's 32 bits, we can just add.
No,
Okay.
right. The 32 bits come in through size, yeah.
Okay, thanks.
Thank you. So I'm very confused by the word parallelism being used here. Because this is all single-threaded, right?
Yes.
Both left and right.
Yes, it's parallelism on a single core.
Parallelism as in better concurrency, maybe like more compact instruction.
Yes, of course. It's both, actually. If you look at instruction level parallelism, you do not specify in what order it happens. But in any case, it's not synchronized. You can think about these SIMD vec types as every element is in a thread, in its own thread. And every operation you do, there's a synchronize all threads, then do all operations on these threads, then synchronize again. Except it's efficient and you don't have to actually wait for anything. Just so if you do CUDA programming, you cannot just simply take a value from another thread. You have to do the synchronize. Here it's different. You can, with a SIMD object, just do all your operations. They are in parallel, unordered, unsequenced, as it's called in the execution policies. But with every semicolon, you have an implicit synchronize. And so you can always just access some member somewhere, and because that's just how the architecture works when you look at instruction level parallelism and SIMD instructions.
So in one clock cycle, one thread can do more than one thing.
Yes.
Wow.
Yes, that's what this is saying. In one clock cycle, you're doing 64 floating point operations per clock cycle. That's a single core. And most people are here. Most codes are.
Yeah. I just have a slightly different question. Why can we merge multiply and addition into one instruction, and why not other?
Why not other?
Multiply,
Yeah.
subtraction.
So this subtraction also works actually. So there's also a fused multiply sub instruction. It's again an architectural thing. It's a question of what does the CPU implement. And if you look at this graph here, the CPU did not always implement that. Back here it did not. Here they added the FMA instruction set extension. And this is also why you have to pass the march flag, because it needs to know that it exists. And once it knows it exists, it will use FMA instructions for scalars and for SIMD. But FMAs is an interesting topic. Maybe you get to that tomorrow when you talk about floating point. FMAs also have a different characteristic in terms of precision, because it's an actually fused multiply add. And the fuse means you do the multiply in infinite precision, and then you do the add, and then you round, which is a different result from doing the multiply, round, add, round.
Yeah, and then one more question. Because if I understood correctly, the reason that the write works on a single thread is because of the pipelining of the CPU. But what are the limitations of, if you wanted to scale this up to more cores, what would be the limitation? Where would the...
Well, more cores is just a different way of expressing parallelism. So you could use threads, you could use TBB, you could use all kinds of abstraction. This is about thinking about the single core, the single thread. Most people think about parallelizing via threads, which is important and necessary, but don't forget how much performance there is on a single core. And I would actually often rather ask people to think about the single core performance before you go multi-threaded, because it also has a lot to do with memory and how you really want to scale.
Yeah, yeah.
Okay, on this one, if you only define your interfaces with SIMD-VEC, now with that thing being part of C++ 26, you may be okay doing so. But maybe you also want a concept that says it could be just a T or a SIMD-VEC T. So it's a float or a SIMD-VEC float. I can use both of them. That's more general. And often you can implement much of the function just with the same code for both of them, because the intent here for the SIMD type is just using the same syntax, same semantics. So you can write the code once for both of these, for T and for SIMD-VEC T. Okay, a bit of an overview of the SIMD type. One variable stores a number of values where that's often called the width. So where we have an int x, we can have a vec int x. In this case, it's 4 values. So this would be on x86, that's SSC. If you get to AVX2, you have 8. If you get to AVX 512, you have 16 elements in one of these. And an operator on it signifies just as many operation element-wise. Just keep that in mind. Every operation just applies element-wise. And that explains all the parallelism here, right? You do it once, and here you do it in parallel, element-wise on all of them, just in one step. The size, so the number of elements, is a constant expression. So you can use it in templates. It is fully optimized because it always knows what it is. And this is also very important if you compare with what's already in the standard for ages called ValArray. ValArray is kind of the same idea. You create this structure of numeric objects in there, and then you have operators that are overloaded in a ValArray and that act in parallel on the whole thing. But ValArray is dynamically sized. And that inhibits a lot of the performance on modern systems. It was more or less designed for the old vector architectures on Cray or something where that didn't matter. You would have huge vectors. You would iterate over the memory every time, and it would be efficient. But nowadays, that's not. You want the short vectors thing, and that's what this provides. And so typically, CPU implements SIMD registers of a fixed width. And then you look at what is the size of my type, and that determines how many elements you get. That's the general idea. Don't rely on that. There are some corner cases where this can break. So if you want to rely on it, static assert that this is true. But in general, that's something you can do. So the definition here of the types vec is just an alias, or an alias template, to be precise, of basic vec, where you give it the element type and optionally a number of elements. If you don't give it the number of elements, it will take the default of what you're compiling to as the hardware register size. T must be a vectorizable type, as it is called. So that's all arithmetic types except bool or long double. Also, at this point, since we have additional floating point types, we have float 128 and float. So float 128 is excluded, and there's bfloat 16, which is at this point not supported, but should be. So I think that might come in 29. Float 16 is supported. Bfloat 16 is not. Bfloat, if you don't know about, it's called brain float. It's for AI purposes. Then there is a mask type. The mask basically represents the Boolean, so the parallel form of Booleans. And there's also the same kind of alias, so you would be able to just say mask for a vector type of ints and then give me either default or a specific number of elements. And what's behind there, this basic vec and the basic mask, is slightly different. So here, the basic vec has, as a second argument, a type rather than a number of elements, because if you think about some of the peculiarities of x86, you come from SSE, you say, give me 8 integers on SSE, that means it's 2 registers. And that's how you would have to pass it to a function. Then you compile for AVX, so you just change one of the M flag or its M arch implied, and suddenly it's 1 register because now it fits in 1 AVX register. And now your function interface would use the same type, but completely different actual implementation of how it's passed. I mentioned this as binary compatibility or your ABI breakage. You would be debugging for a long time. So the intent here is that it becomes a different type. Even though you say vac int 8, it resolves to a different ABI tag. And through that, it is actually a different type. And then when you link, it says, well, that does not fit. I'm going to stop you right here before you get into trouble. So this does help somewhat. It still does not help completely because you can wrap these types inside your own struct that don't have this on their type. And then the struct would hide the fact, and then you could still get the problem. But it's at least giving you a hint and some help in terms of that. If you want to have any kinds of type that wrap these, it's often useful to actually somehow have it part of the type through a template argument and something so that the linker then would fail. And for mask, it's mapping these to fewer types, but just taking the size of a T. That way there are fewer mask types and it's, you need less conversions when they match. How to construct these? You can just do nothing, uninitialized. You get erroneous behavior nowadays. You can default initialize, you get zeros. You can give it a scalar. It will broadcast the scalar. I call that the broadcast constructor. You can give it a range. This range must be statically sized and of the exact same size. In that case, it converts implicitly to this. It also has CTAD on this. So what you can actually do is you write SIMD basic vec s equals, in quotes, hello world. That compiles. It counts the number of characters, adds the 0 character to the count, and creates a SIMD vec of char of this many characters and then copies all the characters into the SIMD. And you can directly start doing string operations on the characters using SIMD. And then there's the generator constructor, which you give a callable like a lambda. It is then called with the element index, and from that element index, you can compute the value at that point. The reason why you want to have this kind of constructor rather than just brace initialization is because you want to be able to just write your code independent for the width that your target will be. So you want to be able to just provide an march flag or go to a different system, and then automatically the number of elements of the SIMD backend will be different. And if you were provide a brace initialization here, you would have to spell out the exact number of elements. And this way it is dynamic. And so the IOTA object, IOTA typically goes from 0, 1 to 3 up, would just scale with that. And you can do all kinds of things here. You can subscript into another vec and do an operation on this. So if you don't know how to do the SIMD operation, just do the scalar operations through the broadcast constructor. And then you're more or less asking the compiler, auto-vectorize this operation for me, figure it out. It often works. I want to look at the load because there are many more load cases. So loads and stores in SIMD act on contiguous ranges. Contiguous is important for performance. If you want to really just get it from different places in memory, that is often just very inefficient. And so while you can do it, you can't do it easily. The thinking or the design idea of SIMD is that whenever it's easy to write, it's efficient to do. If it's inefficient, it will not compile by default, and you have to do something explicit about it. Okay, so I mentioned this, got to be a statically sized thing, got to be same size. If it's not, like you have your std vector of data, you would go to the unchecked load to load from there. There's also a partial load that is safer in a way, but also more costly, that checks the size of the range, and if it's smaller, it would fill the end of the SIMD with the default initialized values. The partial load can be interesting to handle the end of the range. So you would iterate over the whole range in the chunk size of the SIMD until you come to the end, which is then too small. And then you do partial load and just get a very optimized load from there into the SIMD. Stores are just the reverse. So you provide a SIMD object, a SIMD vector, and then store into the range. And then the intent here is that all the operations you would do on float and int, you can just as well do on SIMDVec. All the CMath is specified in C++26 to be overloaded for SIMDVec for all kinds of width. And all these operations just act element-wise. So you have a full understanding, it's just the same, but now you're doing it in parallel on many values. Yes.
By value or const reference?
So the standard does specify everything by const reference because you can completely oversize these things. A SIMDVec default, like a SIMDVec float here, is one register. You can, as I did here, pass them by value. This is a single register. But as soon as you say comma this number of elements, it could be many registers, and then you want to do const reference. So my implementation of limp standard C++ implements all the interfaces as specified with a const ref, but this function itself is declared always inline, so it's forced to be inline even in debug, even in O0. And then the next thing is it dispatches to smaller calls, which then pass by register. So you would, in your application code, see only pass by register calls. There's a question.
Regarding like initializing the CMD vectors, like I suppose that the CMD registers of the core are limited in size. So like what, I mean, I don't know, maybe in the HEP context, if we have like, I don't know, a collection of particles, whatever, or objects that is very abundant, like, and we want to do a CMD operation on that.
Yes.
It's very likely, I suppose, that at some point the memory of the CMD registers is not enough.
Yeah.
To keep in memory all the data structures. So some memory will leak inside the cache. And what happens at that point?
Yeah, good question. So you would still iterate over your range. If you have a range of 1,000 inputs, you would just chunk it into 16 or whatever values fit into your SIMD. Load these 16, work with all of these until you're done, store the result, and then go to the next 16. So instead of your iteration going plus equals 1 in terms of the iterator, you're going plus equals SIMDVec float size, because you process that many. And then there's this tuning factor that I mentioned. You would probably start just with SIMDVec float, the default SIMD width, but you can then try to tune and take 2 of them, 3, 4, and figure out whether any of those give you additional instruction level parallelism, because it's more or less just loop unrolling. Instead of just doing one iteration of the loop, you're doing 2 iterations in the loop at the same time by doubling the size of it.
So there is a fixed chunk.
Yeah. Yeah, you always go in fixed chunks.
And there is a way to know it from the architecture of the
Yes, that's this one. The SIMDVec size tells you the native width of what you're compiling to. Yeah.
Can you go back to the slide 11 where you were? So for example, how does this work with when you were saying that vectorizable types? For example, if you have 16-bit integer, does it also do the same as you said yesterday, where it goes to
Yeah,
32-bit, but
question.
now it doesn't
No.
fit here? So
no promotions.
sorry?
There are no promotions here.
Ah, so it's different from
Yes,
the...
yes, this is different, but still very similar in the end result. Because
Okay.
you would write SIMDVEC short, then do some operation and assign back to a SIMDVEC short. If you do that with shorts, in the end it would just truncate or cut off these bits. The result is the same. So we only use linear promotion more or less for some temporaries and then threw it away in the scalar case.
Yeah.
And here it is, this is slightly different because if it were actually go inefficient and require twice or 4 times as many registers to do the work, that would need to be explicit. And so there is a deviation here that it does not promote.
Okay, and
But
other than
in-
that, does it
in-
work the same in terms of, for example, overflow and...
Yes. So this is an interesting question. For example, shifts, right?
Yeah.
Shifts on a short, since they promote to int, can shift by up to 31 before they are undefined behavior,
Yeah.
even though it's a short. I mapped that onto SIMD, or the specification basically says, because it is the same thing as that would happen for the scalar one. So you can take a SIMD short and shift by 31, it's not undefined behavior. Shift by 32, it is. Which does cost something extra because there are actually SIMD instruction sets where shifting by 15 is okay, but everything above wraps around. And so it sometimes needs some extra work. Okay. More?
I had the question about processing in chunks. So the SIMD vector can like take 8 floats, and we can do 2 floating point operations every cycle. And let's assume that it takes 4 cycles for the floating point operation
Yes.
to finish. That means we are taking total 7 cycles for the entire 4 plus 3.
So if you can issue 2 at the same time,
Yes.
and it takes 4 cycles to get the result.
Yes.
It always takes 4 cycles before you can then issue the next instruction on that dependency chain. And in total, in that time, you were able to issue 8 instructions.
So it's not pipelined. It's like all
It is.
4 operations together.
All 4 operations are in the pipeline at that stage. So you push 2 instructions into the pipeline. There, in terms of the architecture picture there, you have execution ports. And there are 2 execution ports that can do FMAs or floating point operations. And so in each cycle, you can push into these execution ports some work. And then on the next cycle, you push another one. And then this pipeline for this specific instruction is 4 cycles deep. So in each of these ports, there are always 4 instructions executing through that pipeline. And once it's done, you can push from the first that just got out, the next into it. So there's basically 2 independent pipelines, but they have the same behavior.
Okay. All right. Thanks.
10 minutes. Okay, comparisons. There was some contention on this. So people were expecting regularity in terms of the type. Regularity means that when you compare 2 objects, you get a Boolean out of it. Now, what does it mean if we want to be element-wise and basically just express through a type system the parallelism per element? What happens here is also element-wise comparisons. So the if x equals 0, that's like an if many answers at the same time. Because that's the semantics, right? Everything just happens element-wise. So we got multiple answers because there are different values in the elements of the SIMD. So this does not work. the x less than 0 produces a mask rather than a bool. And that mask is not implicitly convertible to bool because there are many meanings. Did you mean any of them is true? All of them are true? Both of them have their use cases. And so you got to be explicit. What you can do instead, you have a select function, which is more or less just like the ternary operator, the question mark colon. So you have the condition on the left-hand side, the true values follow, and then the false values. Compilers actually implement the question mark for the built-in vector types that they use internally. We don't implement that yet for SIMD because we cannot overload question mark yet. I have implemented in GCC. My GCC can use question mark for it. I hope this will be in 29. It's got to be. I have not finished the paper yet. Only the implementation. But also so select is very important because that is what typically then comes up, and it's the kind of branchless computing that is often talked about in this context, because you need to compute both branches and then you blend results from one side and the other one. So you pick some values from the y, you pick some values from the x according to the different answers you got from the comparison. But sometimes you can optimize and say it is fairly common that just all of them are true. So let me take the quick path, and in the case all of them are true, I don't have to actually compute the other side. And then you would do a branch on if all of them are true. Sometimes you would branch of if any of them are true. So yeah, went through that. In terms of a picture, this is the question mark idea. Hope we'll get there. Then there are permutations. I mentioned this. You have this implicit synchronization with every semicolon. So it is fairly cheap to then just permute things across the lanes, across the entries here. And the way permutes are specified is again through one of these lambdas. You get in an index and you compute another index, and that determines how these things flow. Here, this just flips the last bit through the XOR. That means everything there, every odd index becomes even, every even index becomes odd. And so the permutation that we're expressing here is that one. We're just flipping the neighbors. And this expression, if you then look into what the compiler does of it, it's a single permutation instruction that this is turned into. So the compiler has a full understanding of from the index mapping onto certain instructions. So basically it computes this number from this index permutation. So this is a static permute where you at compile time define the pattern, but you can also have a dynamic permute where you have another SIMD vector that determines the indices how to permute. There are also instructions for doing that that map onto these. And then there are memory permutations, which are what I mentioned. If you don't have contiguous loads and stores, you would have a SIMDVec of indices and a range of your data, and then you would, through that index vector, say, take these elements and put them into one of these SIMDVecs. Those also exist as instructions on x86, but they are very expensive to use and slow. In general, if you need a gather or scatter, so gather is the load, scatter is the store. This is a problem in terms of performance. You don't want to have many of these. If you have them, you have a lot of compute come after because these dominate otherwise. Then there are reductions. Like if you have a vector of floats, this is the simple SIMD reduce. You get the sum of all of these in there. It's a parallel reduce, so it does a tree reduction on it. You can also, instead of just using a plus reduction, you can use a std multiplies here. Then you get a product of them. You can reduce with a mask. So this is taking the sum, but it's saying only those elements that are actually positive. You can ask for the minimum in the vector. You can ask for the maximum just as well. You can create a mask and ask what is the smallest index in that mask where it is where the comparison was true. This is interesting for searching. So if you go to something, you say, give me all your 16 characters out of the string. Then you compare the characters against space. You get a mask of 16 answers, and you ask, is any of them true? And it says no. Okay, I'll go to the next chunk of 16 characters. And then you ask, is any of them true? And it's yes. So you branch into and need to find out what is the index of the space. And so you take that mask and what is asked for the minimum index, and it will tell you where the first space is. And then you add that to the offset of the complete string, and you know the position of the character. And so that is a SIMDI string, the vectorized string processing that you can do that way. So this is useful for many search operations. Okay, I mentioned that SIMD is great for computing because you have that much higher throughput in terms of floating point operations, but also integer operations. But that's not all. You also get much higher memory loads and store throughput. Because if you look at the architecture level on the CPU, it can issue, nowadays on x86, 2 load instructions per cycle and 1 store instruction per cycle. Slightly changing, recent processors have done a few other things here, but it's limited by the number of instruction, not by the width of the load or store. So the bigger your load and store, the more the throughput, at least on the cache level, right? If you actually, every time you access memory, it's nowhere in the cache and you need to fetch it from memory, you're completely bound by the latency of the memory, of course. But SIMD is not just relevant for improving compute, it is relevant for getting higher throughput to memory as well.
Matthias, I have a question.
Yes.
I have always taught to students to avoid as much as possible lists. Now, are lists of SIMD vecs performant again?
I did not understand. Avoid what?
I mean, STD list
Yes, okay.
should not exist. I mean, or should not be
There are
used
some,
for performance. There are always ways to make a list vector. Now, if I make an STD list of SIMD vec,
yes.
does it now gain performance and motivation? I mean, in the sense that you are not jumping from scattered memory locations anymore. You are loading a cache line within a node of the list.
I mean, it's certainly a factor of the SIMD width that you would get in performance, because whereas before for every value you had a complete pointer chase, you now have possibly 16 values per pointer chase. So yes,
It makes
between the weights you get much more work done.
I'm thinking of some of the developments that we were doing years ago on CUDA caching not caching allocator, sorry, arena allocation. So you have memory blocks and then with a linked list of memory blocks so that you would still have a flexible allocation, but gaining performance because within the block memory is adjacent. So yeah, no, it was just a...
Yeah, so one thing I did for my PhD, I implemented a KD tree structure where each node in the tree was a SIMD, which was a fun implementation because it was about inserting scalars into it, and so moving parts of the SIMDs down the tree and reorganizing. I did get this quite useful speed up, which is certainly also true because it was less pointer chasing, because there were just less nodes in the tree. But yeah. We're actually in lunch break. Let me run through this. we have talked a bit already about data structures. Just want to get into this idea here. So if you have a point, x, y, z coordinates, and now a function that implements a normalized point, it could look like this, right? T could be a float. I store 3 floats. I compute my scale as 1 over the square root of the, well, that's a hypod 3, right? And then I scale all of these elements so it's normalized. I can create this array of struct from that. So I have my std vector of a point of floats. In memory, it looks like this. I have each point memory next to each other. So all my x, y0, x, y, z, x, y, z. If I now want to put these into SIMD vectors to do SIMD processing, I want to have all the x's in one SIMD vec, all the y's in another one. And so the pattern looks like this. You can see just by the horrible arrow there that this is not optimal for a processor. Well, some actually ARM processors have instructions to do this in just one go. They would load the thing and reshuffle the whole thing, and you just get different SIMD registers doing this. There are also ways to implement this manually on x86. You would do several vector loads and then shuffle instruction, then you have it. But still, it doesn't look optimal, and it isn't optimal. So the thing that has always been taught, and it's not wrong, have a structured array here. Have all your x's next to each other, all the y's, and then I can do perfect SIMD vector loads and vector stores to them. In terms of memory access there, this is perfect, except if I always need all of them at the same time, I lost my locality there. I need 3 accesses to memory, 3 different cache lines in my cache. If I did this in a stupid way, and these are all just powers of 2 away, my cache associativity might kill me. So here's an alternative that is an array of vectorized struct. So look here, I was taking the val array here for saying, okay, this is dynamically sized, but I basically get my vectorized work here. What I did here is I now have a point of SIMDVec. So I instantiate the T with a SIMDVec, which if we go back here, just works. So we have a SIMDVec float for all these 3 members. And if we go through this code, just works, right? Because it's the same syntax, just happens everything element-wise. So what it returns is several normalized points through one function call. You could say this is data structure vectorization and at the same time vectorization of a function explicitly, just through template instantiation. So in memory, it looks like this. I have, in the case where my architecture has 4 floats in a SIMD register, I have 4 x's, 4 y's, 4 z's, 4 x's, 4 y's, 4 z's. So I can do perfect SIMD vector loads and stores, but I also still have my locality. And this then scales depending on what you're compiling for. So if your system has no SIMD support, it would just map to array of struct. If your system has only 2, it would just change the way the data is laid out. So obviously, this is not something you would use for I/O. For I/O, you want to have a fixed interface and binary definition. But for internal data structures, this can be the most efficient way of doing things. Okay, just going to show this quickly. So we have this same point here that I showed before, these 3 implementations of AOS with the data structure, then this SOA using val array here inside, and AOVS as I showed, and these are now my benchmark. So this is when I benchmarked this on my AVX 512 machine, which is quite old. One of the first AVX 512 machines in terms of Xeon. This is the result for the val array, for the AOS and SOA. And this is the result for SIMD on a STD vector. So the val array, I mean, it's not like the best comparison because val array just doesn't always, well, vectorize. But you see, in terms of throughput, getting things done, this is huge. Okay. This is about expressing data parallelism. It just maps to SIMD and instruction level parallelism. Don't think about necessarily instructions registers. Think about it a bit more abstract. You express data parallelism that exists in your problem. Instead of encoding it as a loop that has to go one after another and the compiler then has to figure out, I actually can vectorize this and you did not mean to say this needs to happen one after another. With SIMD, you're saying just do these in parallel. So it enables the separation of serial execution, synchronous parallel, which is SIMD, and asynchronous parallel, which is threads. And I hope that I succeeded in having an interface that guides you toward designing something that is scalable, because the default scales with what you're compiling to, that is portable, also somewhat performance portable, and that enables high-level abstractions, and not just the low-level access that nowadays, if you do SIMD, you often are on a very low level. The goal here is to provide high-level interfaces, and there's more work for me to do also to add to the standard library to add more of the high-level abstractions. And most of the time people talk about vectorization, they talk about the loop vectorization. They look at this specific loop, data exists as it exists, as God-given, and now you have to somehow get these into SIMD registers. Consider type vectorization as well, because data structures is where most of your performance is lost. And then often if your type, if your data layout just already works, then auto vectorization probably also would work at this point. But the SIMD type allows you sometimes to write one of the best way of doing the type vectorization. And if you do loop vectorization and try to use a SIMD type and it just doesn't fit, it tells you you need to do something about your data structures. So it teaches you about what you would need to provide in terms of data structures so that it is just intuitive to use SIMD types, and then it just works. Also interesting here is the aspect of a vocabulary type, so that when you have third-party libraries, you can just talk to them, to an interface that is standardized. And we can start sharing solutions in terms of SIMD implementation, algorithms, data structures, whatever we build, because we can all now speak the same language because we have the vocabulary to do so. Okay, I don't want to hold you longer for from lunch. And then guess we'll be back at 2 o'clock. Okay, unless there's a very pressing question. Okay. Okay, now it's on. Can you hear me? There is sound. Also, the laptop is not.
If you want, I can ask again the
What?
people to raise the volume.
What do you mean?
Ask the technicians.
Okay.
If you want.
I don't know. Possibly.
Time
Yeah. Yeah. So. Okay, at this point, are there any questions, or are you able to just work on exercises at this point? As soon as I have projector up and running, I would be able to do a bit of work on my computer, how I would implement the peak flop benchmark, for example. And I could also try and walk you through a matrix multiplication using MD-SPAN and SIMD. Trying to reach peak flop performance even for a large matrix multiplication. If that is interesting for you in terms of learning, you decide what is good for you to learn something. So I want to do this for you. This is not for me to just do whatever I thought up. But I see some nodding here. Okay, then I would prepare. You can continue, but as soon as I'm ready, I need to sit down. Is this readable in the back, or does it need to be bigger? The smaller I can make it, the more I can see. I like to see as much code as possible. I can't make it smaller, right? Bigger? I can probably. Okay. Okay. So at this point, here in CMake, I have this add benchmark function. It calls it as documented. It has this comment that it would show when running the benchmark. And at this point, I only have defined the benchmark. I have this commented out currently for march native. So I did not put march native into the CMake cache itself. It's not part of every target. In this case, makes it easy to just turn it on and off. Okay, going into the peak flop CPP, this is more or less the start. What I gave you is without these do not optimize. For all of you who have not tried this, what happens here is as a result, we get 3 gigaflop per cycle. Proc cycle, 3 gigaflop. 0 nanoseconds for I don't know how many iterations. So obviously this is wrong. And the reason this is wrong is because it deletes all your code. Because as we mentioned, this is a dead store. It can see X is not used anywhere, and so it can remove the complete thing. So yes.
Just a quick question on this. What does it mean for X to be used? Like, is it enough to just be called by, for example, a print function? Or
yeah,
it's definitely enough, but is it, if it's just called by another variable that is then not used, is it also enough?
Something I sometimes do is, for example, say I have here my black hole where I put stuff, and you can just in the end store it there. This is also going to be used, right? If we look at this, we get a sensible number of point something flop per cycle.
But the black hole needs to be outside of the...
Yes, because otherwise the optimizer can see that it's not used, and then it says black hole is not a black hole. So put it outside. If you put it inside, you make it volatile. That will also work. Because volatile is basically saying there are side effects when you write to it. Like there is some hardware behind it that will act on this. So writing into a volatile, this also makes this work. But do not make the X itself volatile. That leads to way more work, because then every time it modifies the X, it has to actually store it to memory and then reload it when it reads it. So that it would be very different results in the benchmark. In general, I would recommend to avoid volatile. You see the flop per cycle went down now. I would like to avoid volatile wherever possible and just keep volatile for what it's used for, access to hardware, where you then talk to device drivers. Global variable is enough because, again, similar to volatile, looking just at the peak function, the optimizer does not know whether this is going to be read somewhere else. It could be even a different thread through some synchronization method that it does not see here in this locale way, that this is read in the end. So it would need a full application optimization where it would potentially be able to say global is also dead store and I can remove it. But that does not happen because you could have like an LD preload that starts to actually read it. You could have some extern float black hole somewhere else that you really can't see. And then, so yeah, globals typically work for stopping optimization. But the documented way of Google Benchmark is just to use do not optimize. And the reason I added here is you could think that it sees, okay, float is 1. So the next step I can pre-compute, and the next step I can pre-compute, and the next, and so on, right? The reason it cannot actually do it is because it does not know how many iterations it will go. If it knew, if it were a fixed number of iterations, the complete thing would be replaced by the result of the whole thousands of iterations you would give it. So it's often just better to just say, well, I gave it a fixed number, but I'm hand waving, optimizing, you don't know what it is. Behind this do not optimize is a inline assembly that does nothing. But to the compiler, it says, I'm reading this value and I'm changing this value, even though I'm not, but you have to assume. And so this is an optimization barrier, which is why it's named do not optimize. Okay, so we do get the whatever, why it's not 0.25. I probably need to run my benchmark script. Let me just benchmarking on. See whether we can get a different result. No, it's still, I don't know why it's a third in this machine, but if I now go to the CMake list, turn on marchnative, recompile and run it, we get to see the 0.5 here. Right, so that enables the FMA. Now let's go here and make this a array of 8. And I'm just going to initialize these with zeros. So I have less typing to do. And now I need another loop here for all whatever float y in x. Okay. What do you mean? I can't hear you.
No, the reference.
Oh, yes, you are right. I need a reference, otherwise I don't modify it. Then it can delete the code again. Okay, I'm still seeing the 0.5. So this is not running these in parallel. Let's take a look. So this is my code section. So this is how I work. I just open my binaries in Vim. It disassembles for me. These are my setups. Understanding how Google Benchmark works, looking at assembly is not easy, which is why I often use my own benchmark methods, because it's hard to find from here, it's starting here, it's ending, and this is a section that is getting benchmarked. It's hard to figure out, so we'll need a bit of time here. Okay, I can at least make it easier by removing this part. So we have the FMAs here. We see this is getting, or I see that it is getting vectorized because it's saying PS. P is for packed single precision. If it is saying SS, it's scalar single precision. So these are acting on AVX vectors. YMM tells us these are the bigger registers, which are the largest ones available on this laptop. We have 3 FMAs. And this is the loop. Okay. You see what I did wrong? I see it now. Because you actually, we told it we're doing 2 flops per iteration, and we're not. By now we're doing 8 times 2. It's just the interpretation of the whole thing, right? Because it cannot actually measure the flops itself other than potentially looking at performance counters. But in this case, we're only looking at the number of cycles and the number of instructions and of the time that we're taking. So we need to compute this correctly. And that's the only problem here. Okay, that's 4 flops per cycle. So now let's try how far we can get, because we saw it was actually doing vectorization by itself. It's getting worse. We just wanted ILP. We didn't. So what happened here? Okay, so that gives us a first hint. It's starting to use the stack for lots of things. So it's initializing the stack with all these I don't see there's an FMA. It's the only FMA. Yeah. So it is now jumping to here. So this is our loop. And it's basically bound through the loads and stores that it is not efficient. So it's instead of what we wanted it to translate it to, that it works just on registers, it decided, well, your array is so big, let me just put it on the stack and then load and store from it, which just killed all the performance here.
So what is that?
Okay, so the FMA instructions take 3 inputs and 1 output. So it's actually 4 arguments that you need to give, right? It's A times B plus C and then a result. But the instruction encoding only has 3 operands. So one of the operands is read and write. And so in order for the compiler to have more freedom, which one is the read and write register, and also which one is the one that it can take from memory, because it's only the last one that it can take from memory, there are possible orderings of which one is multiplied by which one and which one is the add. And so 1, 3, 2 says multiply 1 by 3, so we're multiplying 0 by the thing we're loading from memory, and then we add 2. And that's what it's. So there was originally an FMA implementation by AMD, which was then also called FMA4. It had 4 arguments, and that was not picked up by Intel until it did its own ISA extension that they called FMA. And then Intel had to follow that, and Intel dropped the FMA, AMD dropped the FMA4 instruction set. Bit of history. Okay, so this did not work out. And let's try with SIMD. Yeah, let me use that. Okay, does that make sense to you? We're initializing now a default sized SIMD register, so it's one register, whatever the target hardware is. We say you don't know what the value is. We iterate over two operators, but these operators now act on multiple values. So we again need to make sure what is this number here. This number at this point we know is a SIMD-VEC float size, right? Because that's how many elements we're acting on element-wise. So let's see. Okay. Whatever you're, right. Okay, something about conversions in SIMD that I did not mention. SIMD is stricter about conversions, whereas I told you fundamental types just implicitly convert in every direction. In SIMD, that's not the case. You need, for implicit conversions, a value-preserving conversion. So an integer which has 32 bits can have values that are not preserved when you convert them to single position floating point because it only has 24 mantissa bits. It is value preserving convertible to double precision because that has enough mantissa bits. So a conversion from int to double is fine. What we do here is just make that floats. Once these constants are floats, the conversion from float to float is fine, obviously value preserving, and this works. Okay, so we're back at the, well, almost 4 per cycle. Now let's make it bigger. Let me X per int and equals in back size. Let's try that. Oh, wait. We need to interpret it correctly, right? We just made it way more elements, so okay, our flops per cycles went up to 27. Why do I not get the full speed? Okay, so this does look much nicer now. And we're going here to this address. So this is our loop. Looks kind of perfect loop to me. It's just doing FMAs. It is reading from registers 1 and 0. These are not modified, so it's not doing any memory access, and it's modifying these YMM registers here on the left. It's reading and writing from them. So we have obviously 8 of them. And then there's only this one variable that we count down. So this is just initialized to the number of iterations we're going to do, and then it's going to decrement that. And once that reaches 0, the 0 flag will be set, and this jump here tests for not equal. So it's testing for the 0 flag, and as long as it's not 0, it will jump back up. So this loop is just going all the way until RBX reaches 0. Looks like the perfect loop to me. I don't know why it's not showing the performance here, possibly.
The fact that it's in the middle of the late because then it's applies to this
at this point, it wouldn't matter. This is just, it would be okay at every point. Potentially, it could be better if it's moved just directly on top of the jump, because there is so-called micro-op fusion in the CPU. So whenever the CPU decodes your instructions, it then decodes them into actual micro-ops. There is some kind of abstraction still in the CPU. The assembly is not what it's actually executing. It's still some kind of intermediate language. And it is translated by the front end of the CPU into micro-ops. Some instructions are multiple micro-ops, like obviously the instructions that take a memory address. So an FMA that also loads from memory is one load micro-op and one FMA micro-op. In this case, all of these are single micro-ops, but there are also some special cases where it fuses micro-ops into a single one, and especially the test and jump are the ones that are actually fused. I don't know whether sub and jump would get fused. But these are things that you don't need to necessarily care about. That's something the compiler knows and models and would try to get the best out of it. If you really need to get into why are the performance numbers as they are, then it's useful to get into this. Also interesting to know, the CPU has a certain cache for loops. So in terms of decoding these instructions, it will decode them once, and then they are in a cache of micro-ops that where the loop is short enough, it will not have to decode the whole thing. It will just work from there. So this is maximum efficiency as you should be able to get here. Just still wondering why. Doesn't get better. So potentially this is running on my Atom cores here. Okay, go away. So I might want to use the SCED tool. Who remembers the invocation? I don't. This is what I want. Okay, so now I'm forcing this to run in SCED FIFO with real-time priorities so that no other process can say, I need the CPU, and the kernel would say, okay, just wait a bit. Benchmark, you're not important, wait. And that would skew our numbers. And more importantly, we want to say on one single core and not migrate. Especially, we do not want to migrate to one of these laptops' power efficiency cores, which are Atom cores. They have very different performance characteristics. So let's see. Yes. Now we're seeing better numbers. And if I turn benchmarking back on, maybe even better. Let's see. No difference. Yeah. Okay. So what is the theoretical limit that you can achieve? Yes. You need to look at, where did I link to this? I think this one. Microops.info. Very interesting stuff. This one is basically documenting for x86 and also for all kinds of different architectures and for different wherever that information can come from, the information about latency and throughput. So looking at FMA, we need to enable FMA instructions. We have all kinds of different FMA instructions. So let's be precise here. We want the FM add 132 just for, right, and it's a PS that we care about, and it's the YMM. So this one is taken from memory. We don't care about this, so we're looking at that one. So it tells us it has on the Skylake, which is, this is not a Skylake, but what is it? Yeah, it's probably close to Alder Lake. Anyway, it's the same. Latency is 4 cycles. Throughput is half a cycle. So in theory, the throughput is the only thing we need to look at here. Tells us we can do 2 FMA instructions of full SIMD width per clock cycle. So if an FMA has 2 floating point operations on 8 elements, that's 16 elements times 2 because of the half 0.5 throughput, that's 32 floating point operations per clock cycle. This is what we can read out of this table. So the theoretical limit is 32. And on my AVX 512 machine, we need to go to ZMM here. We see basically the same thing. It's 0.5. So the only thing that changes here is the register, which is double that. So instead of 32, it's now 64 floating point operations per cycle. So this is where you can get your theoretical limit from. Also in terms of loads and stores, right? If you take the SIMD width, that tells you on an AVX 512 system, your SIMD width is 64 bytes. You can do 2 loads of them per clock cycle. If we look at the move apps from memory, that's 0.5. So we can do 2 loads per clock cycle of 64 bytes. So that's 128 bytes per clock cycle. Multiply that by your gigahertz of the system and you know how many gigabytes, close to terabytes we're getting. That's only level 1 cache into registers, of course. Once you're in level 2 cache, you have at least latency, but also some throughput. At level 3, level 2 cache, level 3 is definitely also limited on throughput. If we want to look for the stores part, we make this M512, and you see for the stores, the throughput is 1. So that's half of that, which is kind of what typical applications do. You need 2 inputs, 1 output, right? X plus Y. So 2 inputs, 1 output. So that's what they are optimized for. Okay. I don't know why I don't reach 32 here. Like I said, the assembly looks perfect, but it's pretty close. Okay. At this point, do you want to play with this yourself a bit, or should I go to matrix multiplication? What? I continue. Raise your hand if you want to see a show. Okay. Yeah, it's as simple as that. Okay, I'm just adding that benchmark now, and I will from the start just use MArch native also for GEM. GEM is short for general whatever matrix multiply. You possibly heard of DGEM and SGEM for double precision and single precision. We're doing both at the same time because I'm using a template here. Yes? So what I sometimes do if I'm searching for my assembly is I insert some inline assembly that says, I'm starting here. And then you can't assemble the thing because the assembler says that's not an instruction, but the compiler is fine. So you can use the compiler to output assembly and then stop. And then you can look at it. It's also an interesting trick on Compiler Explorer itself. You can, if you have a constant expression and want to put that value into the output of the assembly, you can do so using inline assembly. There are cases where you otherwise would not be able to see it because you were doing some generic stuff, but I can then like put markers of I'm here. So in inline assembly, you can put all kinds of strings. Let's just do that here. Take a little while. That's fine. The compiler doesn't care. When you say I'm doing inline assembly, you're saying I know what I'm doing. And then it's the assembler that said, no, you don't. But the compiler doesn't care. Okay, so let me try const expr int I equals 1 and think it works like that. I don't recall for sure. Yeah, there's our one. So you need to learn how inline assembly works, but basically you can sometimes inspect stuff. This is otherwise invisible. Okay. Now let me. Okay, so I wrote this matrix multiply benchmark before. Let me try to walk you through parts of it and hide some code from you first. Like we're going to do the non-SIMD part first, just looking at the MD span. Yeah. Okay. Okay. So starting from the bottom, we're adding here the benchmark calls. I added also a benchmark for float 16, which is only enabled if the hardware actually supports it. So it's not enabled on this system. Then we're going through this benchmark with a certain range. The range here is the size of the input matrices. My matrices in this case are just same length. So that simplifies some of it, but it doesn't necessarily have to be. And when we're going through the code, we see that we're taking all kinds of rectangular sizes out of that. So we're going up to 8,000 by 8,000 matrices that I'm going to multiply here. This is reaching the level outside of the cache, completely outside of level 3 cache. So it is really completely in memory, and it is memory bound at this point. And I implemented my own range. There is a pre-defined way of going over a range of inputs that goes into certain steps that I did not want. I just wanted to double each time, so it's I plus equals I, so it's times 2 basically every time. Okay, and then it goes into the benchmark, and now here this argument that we're iterating over is in this state range 0, so the 0th argument to the benchmark, and this is now an integer. So this is not constant expression. This is part of this argument, and like I said, function arguments are never constant expressions. Okay, now from there on, I'm creating a page-aligned resource. Can I easily remove this? Yes, for now, let's remove this. The vector of zeros. Okay, yeah, just. Okay, so I'm creating vectors, split vectors of type T. The type T is determined down here to be either float or double. And I'm calling them A, B, and C like you probably would when you write down math. And the size of it is, well, let's also simplify this to n times n. So I'm getting exactly the size of the matrix number of elements, of float or double, and I'm initializing all of them to 0. If I were using braces here instead of parentheses, I'm getting in trouble. Okay. This is still using Mersenne twister, but it's not important now. Uniform distribution of values from -0.5 to +0.5 that are filling the whole matrix with. This distribution called dist, I'm using it here to initialize all the values in A and B. Okay. So, okay, this is syntax. Yeah, sorry. In C++ 26, this is a new construct that you can write a for loop which has a template in front. So normally in a for loop, this I would be not a constant expression. Here it is because it's a template. So it's not actually looping. It's not like if you look in the assembler that it jumps, but it instantiates the body of the loop every time. And I'm instantiating it with values from, well, okay. So a SIMD IOTA object, it's the first feature that went to C++ 29. It just didn't find enough time to finish it in 26. Should have been in 26. It's part of the lib standard C++ implementation, but it has two underscores in front of it because it's not standard yet. We're creating an IOTA object of a SIMDVec with 13 elements. So that is 0, 1, 2, 3, 4, and so on up to 12. Because there are 13 elements. Then I'm adding a 3, which is very nice. So it goes from 3, 4, 5, right? And this is my index vector that I'm now templating for over. So array space for instantiation of these constant expressions. I need this because this n here is not a constant expression. I need it as a constant expression. And so I'm simply just iterating over it and saying if my n is my n, so my constant expression n is the non-constant expression n, only then do I want to actually do this work, right? It's a poor man's mapping of that thing which I wanted to have as a constant expression into a constant expression. So kind of a hack here. But for a benchmark, hacks are fine if you get to measure what you want. So run and verify. After I created two matrices or backings for matrices at least with random values, I'm going to run and verify. Now I pass this constant expression n into this as an argument of the templates. Pass also on the benchmark state and the backing store for A, B, and C. Okay, let's go to run and verify. So here I'm taking these as spans. One of them is const, the other two are, well, I don't know why that const should be, well, it's at the wrong place. Okay, now I need to simplify this again. We want to just at this point take the default layout. The default layout is layout right. So let me just disable the whole thing and take this away. So we're creating a simpler MD span here. Two of them are const. Those are A and B matrices, and C is where we're writing to. The A and B matrices take as backing store what we get from these two spans, and we're saying the extents in 2 dimensions is n and n. At this point, the n can be non-constant expression, but at this point, we're creating the extents. It cannot be. And for MD span, this is really interesting if you have static extents. Once you have static extents, if you then take sub-MD spans out of it, so if you have a huge matrix and you want to do matrix multiply, you can just always split it up in sub-matrices and then treat these matrices as elements of a smaller matrix that you just do the matrix operations on to do this, right? So I want to have sub-matrices here. And in order to then efficiently index over their elements, if I have all these extents as constant expressions, then it can do all of this at compile time. And the final one, which has multiple steps of going smaller, is not a complete waste of resources just to compute the indices, but it's fully optimized to just simplest thing in the end because it was all just constant expressions that went through the whole thing. So that's why this is here. Okay, and this is actually my benchmark loop now. I'm setting the C matrix to 0, which is part of the algorithm because I'm going to now accumulate on the elements of C. So I need to start with 0. Otherwise, if I accumulate on something's uninitialized or whatever was there before because I did another operation, would be wrong. Then I do the matrix multiply, and then this is like a do not optimize, but a do not optimize in a global sense. Like I'm reading and writing all memory that you can have access to. This is like I don't have to specify which variable I'm touching. I'm just touching everything. Okay, and in the end, here's an actual verification that my matrix multiply did the thing that I expected if I do a stupid implementation of it, or stupid in terms of performance, not necessarily. And then flop counters, IPC counters, just to get more information. Okay, so the magic happens in GEM. Let's take a quick look at zero matrix. It's a simple stood fill with zeros over these iterators here. So we're zeroing the backing store here on CDAT rather than taking the empty span. Okay, let's go to GEM. Not that one. That one. Okay, so this is as a first parameter taking basically an out parameter because here it makes sense. We want to say don't create a new matrix that is super big. I already have one in memory. Here's a pointer to it, and we're using the empty span to do so because this one is not const. And now these two are const, so these are read-only. Notice that I did not use constref for empty span. I'm not sure whether that is any problem, but in terms of what the benchmark shows, it doesn't seem to be. Anyway, so now I'm doing some magic in terms of how do I, if I have a big matrix, go about compiling this into smaller things. And this is where the cache hierarchy comes in, which is why these are named L1, L2, and L3. These are numbers I took from my system that a core has available in terms of how many bytes are there in these cache levels. And then I'm checking if the size of the matrix that I'm currently being instantiated with, so n times m, which can now be different at this point, is smaller than the SIMD width and the number of registers that I can hold at the same time. And now we go up here and see n registers. So on 32-bit x86, it's 8. With AVX512, it's 32 registers, and otherwise it's 16 registers. Again, something you need to look up in your CPU documentation, but this is like the tuning factors that you can build on. Okay, if it is basically small enough, my matrix that I am looking at right now, then I can go into the actual smallest vectorized matrix multiplication. We'll go there in a bit. For now, just look at the recursion we have here. Here it is just computing for however big our input is. So input bytes is taking the size of the T times all three matrices. So it's considering all three matrices that it's needing to look at. This is the amount of memory that I need to work on. Does it fit into L1, into L2, or into L3 cache? And on these conditions, I'm determining new sizes for M, N, and K. So for the different dimensions of these of the matrix multiply. And then I'm going to iterate here and create a slice out of the matrix that I got from C, A, and B. And these slices, we go here, is just a call to sub-MD span. So sub-MD span takes an existing MD span, gives me a new MD span, which is just a view into the same data, but now with different strides. So whereas before the original was just going linearly through the whole thing if you were going in the right direction on the indices, now if I take a sub-MD span out of that, that is smaller in one direction, it would have like read contiguously in one direction, and then it has a stride to jump over in the backing memory before it reaches the next line where it then continues. And these kinds of stride calculations so that it creates the correct layout mapping for the MD span that it has to create, all that magic happens in sub-MD span. So you have less work to do. The important work you have to do is to provide these extend slides. There are, to sub-MD span, different options of how you can specify what kind of sub-MD span you want to take out of an MD span. In this case, I'm providing through this construct here, the CW, which is a shorthand for constant wrapper, a type that we introduced in C++26 explicitly to be able to pass a constant expression as a function argument. Right? Function arguments can never be a constant expressions, except here. Because what this does, it is, look at this, this is a template parameter, right? It is creating a type that holds the value of the integer, and now the caller deduces the type, or is instantiated with the type that holds a value, and we can then extract the value from the type, which is a constant expression. So this is a trick that works in many places all over C++ now, the std_cw. You will see it starting with C++26 to appear in all kinds of places. It also works for SIMD where you want to just divide by 2. But 2 is an integer, it doesn't work with floating point. Then just divide by CW2 and then it works, because it can then actually see the value and see the value. Well, that is value preserving to convert to a float. Anyway, so we're passing these as constant expression into the extend slice, telling the sub-MD span to create extents that are, again, constant expressions rather than runtime values. And so if these are runtime values, it has to compute so much more for the index calculation. And this way it creates like the perfect MD span definition so that it doesn't have to do any extra runtime work. Okay, so this is like recursing like crazy. We're doing these for loops and we're just recursing through this gem implementation. This function recurses to itself, just making the matrices smaller and smaller and smaller until we reach the point where we can go to gem back. Now we want to see the meat. Let's do the simple thing. In the simple case, in the scalar implementation, we don't actually explicitly vectorize the thing. Well, we simply iterate over, okay, now I'm using IO array. This thing is something I introduced into libstandard C++ as a helper. And in 26, you should be able to use a std index sequence to do so, but there are some implementation problems, and I'm not sure whether it works in the latest versions of the released compiler or not, but I wrote this so I know this works, and I just used it. But the reason I use this for range base 4 is so that I can experiment with template 4. Because when you put a template in front of this, it's like an explicit loop unrolling. The compiler is now forced to completely unroll this loop. And that was interesting just to experiment with what does it do if I'm forcing that. But the straightforward way is to just have these 3 nested loops over the indices, and then this is more or less math. This is how you would do the index based matrix multiplication, right? You probably recognize this as C under subscript ij and so on. Right, so this is straightforward. Now let's try, okay, we're defining no SIMD, so this is true. This is also true because 1 is true. And so we're getting into this section. We are not getting anywhere here, which is the code I've hidden. So let's see what that, oh, I can, wait, I need, no. Where is my gem? Still not there. Did I not store? I think I did not store my CMake list. Oh, come on. Yeah, that helps. No sources. Yes, that would help. Okay. Yes, here we are, run gem. Okay, the page align source. Okay, we're not, even though we're not using it, let me just get this. We'll get to this in a bit. Yeah, so this is using an old interface from Google Benchmark. It still works, it's just deprecated why I got this warning. Okay, now we're seeing this benchmark running for the different sizes for the matrix multiplication for floating point, and now it's getting big, slow. But the flop per cycle, I mean, the theory is 32, right? So, not much. Okay, let me stop this. It's going to take long. I'm going to make this smaller here so that we can get somewhere. In the meantime, let me okay, flop per cycle is just looking bad. Let's stick to no SIMD, but take another branch here. A smarter implementation, but still we're not using SIMD. Okay, so you're seeing here flops per cycle 0.7, 0.7. This is sad. But look at the IPC. So IPC is the instructions per cycle. It's maximum. It's like, I mean, between 4 and 5 instructions per cycle. Time. It's just not being efficient at the work it does. So let's at least look at how we compute the flop counters here, and whether you agree this is correct. So we're computing 2 times n minus 1 times n times n. So the complete matrix, if you think about it, is full of FMAs, right? You can continue keep thinking about it. I also asked AI whether it's correct. I looked it up, I think, on Wikipedia, whether it's correct for matrix multiplication. I think this formula is correct in terms of how many flops the whole n times n matrix multiplication does. And it does not change with anything we're doing because it's just n times n. It's independent of how we're implementing it inside, whether we're SIMD or without. It's just a property of the matrix multiplication. Okay, let me close this so we see more. Okay, now I disabled the simple loop and we do something smarter here. We're creating something I call V, which is more or less like a vector, which is now an array over T in the M dimension. So our M dimension is the one that matches between C and B. And here we're creating another array for all the rows in C of type V. So this is an array of array. This is getting close to what you're kind of want to do in SIMD. We're just now basically giving the compiler a chance to auto-vectorize the whole thing. Because we're creating local copies. Consider the following. All these MD span accesses are accesses through pointers to T. Every time we store into the C matrix, we write through a pointer to float. And then it needs to read from an A or a B matrix through a pointer of float. How does the compiler know that the store to C does not change the value in A? The compiler does not know. The compiler must assume for correctness that every store to C changes the value in A and or in B. So every store invalidates every load, and you cannot reorder them. Especially that means you cannot vectorize them. Because if you would take multiple and load them, work on them and then store them, it would be incorrect if the store would have overwritten one of them because it would have been a different result. That's why this simple implementation is really already hard for the compiler to prove I can vectorize this. So we're helping the compiler by creating these rows, and now we mem copy out of C into these rows of C which are local variables. Now if I change that, the compiler knows this is not going to change A or B because this is a local variable. These cannot possibly point to the same memory. This indeterminate attribute here is new in C++ 26, and it was introduced because of erroneous behavior. Because this is an uninitialized variable. If I don't have this here, the compiler emits a mem set to 0. Because it does not know for sure whether I'm going to overwrite all of it. It's somehow not looking through this. So this mem set to 0 and then the following mem copy is of course slower than just dropping that mem set. So I'm dropping that mem set by saying, I know what I'm doing. Don't do your dance with an erroneous behavior and initialize this. So there's a way out in terms of performance. Okay, so we're copying all the rows of C. And now we have our loops, and the inner one is explicitly unrolled, basically asking for vectorization. Because if you look at the J index is the last index of this rows C, and the last index is the one that is contiguous in memory. So we're saying take all these values that are next to each other basically at the same time. It's more or less like saying, this is perfectly vectorizable. You should see that. Please do. We have also tried as hard as possible to tell the compiler via extensions that these pointers do not alias. Whatever it's reading there, it's never going to be changed by anything. You're the only pointer to this value. So that's what this restrict is trying to say. This is actually a C feature that never made it into C++, but compilers implement it anyway. It just never worked for me. I try anyway. Okay, so we do all these operations here, and in the end, when we're done, we need to copy those local C values back into the C matrix. Okay, now I enabled this, and let's see what happens. I see I only have 15 minutes left until time's up. Okay, I don't have memcopy. Why don't I? Well, come on, memcopy is part of what? Memcopy is in C string, oh, C string. I'm not used to using memcopy. I always use built-in memcopy. Yeah. This is like the inner hot loop that is like super optimized. So I know it feels like wrong. Yeah, sure it is. But. Okay, so this does look better. Look at the flops per cycle. And we're actually at double already. This thing is much faster. Okay. So, okay, flops per cycle, 4, 6, 7, 6. And then a double, this is half a, it is doing something. It is better, but still far away from 32. Okay, let's try to do better and go to SIMD. Yes. Ask. Yes. Just without it, it is already indeterminate. Because right now, if you don't initialize something, it is just not initialized. Starting with 26, it's going to be initialized because of erroneous behavior. And so that's why you only need it in 26. Okay, now here the difference is my V is now not an array, but a SIMDVEC. And the SIMDVEC is simply the whole dimension of that matrix, the whole thing. So basically, take a complete row out of the matrix as one SIMDVEC. The size for M is specifically chosen down here to be, well, 4 times the SIMD width. So I'm taking almost the 8 that we saw for peak flop. That's a factor 2 difference. But yeah, there's other unrolling that's happening here. Okay, so I don't recall what n strides was. Maybe we come to that. Okay, now we create the rows, again, indeterminate, and now we do a SIMD load for this thing per row from the C matrix. And I can actually add this extra feature here, say this thing is aligned memory. So that should not change much of the performance, but for some of the very hottest loops, the difference whether I use an unaligned instruction or aligned instruction can show up. The way I created my code, well, not anymore. I removed that part. Let me get that back here. I wanted aligned memory. I need aligned memory. Okay, I need the resource and now PMR. Okay, just a word about this. So, okay, PMR vector. PMR is the polymorphic memory resource thing. And basically all containers exist in that namespace again. The difference is that the default allocator is not the default allocator, but it's a polymorphic allocator. The polymorphic allocator can be whatever you then choose at runtime. The interesting thing you can choose here is something like this page-aligned resource. You're just quickly going to show. This is derived from PMR memory resource, and it provides these do allocate, do deallocate, and do is equal functions. And the functions basically just fall back to the global operator new, so I'm not doing my own memory management really. The only thing I care about is a certain alignment. So I'm using the special overload where I pass an alignment T as a second argument to operator new to ask for a specifically aligned memory. So that means I'm asking for alignment to 4096 bytes. That's the smallest page size that you would get on x86. Typically, for huge pages, you can get larger page sizes, but I thought, well, let's go with a small one here. So I'm sure that my alignment is at least that. And the way I then go into the submatrices, my alignment is at least always vector alignment because I make sure that it's always a multiple of the SIMD width. And then this is just the deallocate, the delete equivalent, and yeah, just what I have to implement here. So this resource is then passed to the PMR vector, so that's how the vector now allocates its memory. Normally, the STID vector would allocate by whatever is common to your ABI, which is 16 bytes. 16 bytes is not enough for AVX. There I need at least 32 bytes. I really wanted page aligned, or at least cache line aligned for matrix multiplication purposes, so that's why I'm doing this. Okay, now I can actually make use of this flag aligned here. Before it was wrong. It could have crashed my whole program. Okay, now just this is copying the rows. I could have also written mem copy here, but because mem unchecked load is basically just implemented as a mem copy, but this is the official interface. Okay. Right, so this is another optimization in terms of the strides. So depending on the very small matrices, the sizes are potentially too small, so that this M is problematic. Let me, I don't recall which ones was what. I think this is the general case. Let's just go through here. So start from the inner one. What we see here is we just act on the whole row. Where before we had I comma j, we don't iterate over j anymore. Because the j is just part of the SIMD, and now we're just doing the whole thing in parallel. So all the j's just happen in parallel. That is true for the rows, which we explicitly created above, but also the b's. So if you look here, bk is a complete row of b that we just load starting from 0 with the whole width of M. Again, flag aligned for aligned loads. And so this is our B row. And now we only need to iterate over all the rows in C, so over all of I's. And this access into A is a scalar because we actually do the multidimensional access into A. So we get a single scalar multiplied by a complete row of B. So the A will be broadcast. That's a broadcast constructor into SIMDVec, and then we have all the same values, all the same A's multiplied by the complete row of B that provides us with the result that we need to add to C, so accumulate onto C. And there are n rows of C where we have to do this, and this is explicitly unrolled through the template 4 here. And here this has been just some trying how to go in what kinds of steps so that the compiler does not start spilling registers onto the stack. I really wanted to just keep everything in registers. Once it starts doing extra loads and stores, I lost, because I want all the loads and stores to be only working directly on the matrix A and B that I'm loading from, and all the stores just go to C, because I'm really bound on these in the end. So this is one of the cases where in the end, either you write it in assembly, or you look at what the compiler does in terms of disassemble the whole thing and then figure out what is the steps you need to take so that it does not start spilling onto the stack. It's a bit sad that it is that way, but okay, let's try that. Need to figure out how to write this differently. It's running. Yay, look at the flops per cycle. Okay. So we're getting closer to the maximum. Let me go to large matrices now. I will not reach peak flop. But at least look at the larger ones, because this is instructive how this how the caches affect this, even though we have only 6 minutes left. Okay, so this is the small matrix cannot get full peak performance, and now the bigger matrices, these are extra because I'm not doing the verification anymore. The verification takes too long. For the bigger matrices, it's now getting slower. Taking a long time. So do you know why it gets slower for the bigger matrices? Simple guess. Well, I don't do more loads. Well, certainly more, but not relatively more. Yeah. Yes. Yes. It's actually already pretty optimized, because if we look at the way I'm going through this recursion here, I'm already looking at all these different cache sizes and make sure I block on these. So the way that this goes to smaller and smaller matrices, it goes into sizes which completely fit into L1 and then does the complete matrix multiplication in there. So as long as it's working in there, it's like perfectly cached. And then we go to L2 size, take the next one and go there. And then we do the basically on these submatrices a complete matrix multiplication. So we keep L2 unchanged for the perfect time. You can't do more on this working set. Then we do the same thing on L3 and recursively go back into the smaller sizes. So through this blocking mechanism, these recursions that this calls itself, basically the cache is as good used as could possibly can be used, right? This is blocking, as it is called. If you would unroll the whole thing or expand the recursion, this is like, I don't know, it feels like 16 for loops nested into each other. Kind of crazy, but this is more efficient. Where this actually hits us is cache associativity. Now I don't recall what I deleted. Let me go back to the original I had here. Right. So I need the layout here that I add. Okay, so in here we are using now a specific layout. Before it was just using by default just layout right. Now we're using a layout right padded with an extra cache line size. Cache line size is trying to match exactly one cache line, which is 64 bytes in this case. And that is part of something I do here in the allocation. Okay, I can close this again. So when I now allocate my backing store, for every row, I add extra 64 bytes. These extra 64 bytes I don't use. I just keep them there so that the next row does not start as a power added power of 2 from the original one. Because what you do if you take a submatrix is that you take them at the same point, right? And so if all the data in there starts at the power of 2, you're effectively making your caches smaller because of the cache associativity. This is something, if you have not learned about this in university, I can teach you this in 1 minute, so I won't do it. You either look it up or it's in the following lecture. But this basically effectively makes your cache much smaller by whatever the cache associativity is. And so by adding one more cache line, everything is just scoot a bit, and now I don't have that problem anymore. Let's see whether that is visible. So the question is, how bad does it go down? It doesn't go down as bad. So it was 17 float per cycle before, and now we're up at 20. So that's quite a bit of compute in terms of these big matrices that you just can get by adding a bit more memory to your backing store and just computing your offset slightly differently, and suddenly you get not factors, but certainly visible percentages of speed up just because of cache effects. And it's 1/2 past.
Is there a way to do the cache size or actually
you wanted a compile time, right? Not that I know of.
without actually looking at
So the compiler has compiler flags where you can tell it the cache sizes, because the compiler also has certain methods of trying to optimize for caches, but I do not know of any interface of getting that out of the compiler into C++ code as counter expressions. That would certainly be interesting. But the compiler still doesn't know, because if you tell it just march native, it might be able to just look it up. But if you just tell it march skylake, there are different skylakes. Yeah. At least the cache line sizes are now part of it. You have this constructive and destructive interference size in C++, which are basically the cache line size. If you start using them, GCC will warn you about this is ABI breakage just waiting to happen, which is then you say, yes, that's what I want, because I want to optimize my thing depending on what I'm compiling for. But yeah. Yeah, also this kind of constant here, the number of registers you have available. It's also a target feature that I would like to query. Yeah. Yeah. So this is what we have right now. I think at some point I had some better numbers on this laptop, but yeah, but not much. I did not reach peak flop performance with this. Yes.
You gave the way to calculate your peak performance when you're not taking into account you're going past the size of the caches. How would you calculate? Like, is there a way to make it a more complicated formula that takes into account the fact that you're loading from memory, etc. And
not sure what do you mean?
Well, for example, you can see the performance going down because it's getting larger for flops per cycle. I mean,
so you can always consider the larger the matrix is, the more you don't do the actual FMAs.
Yes.
But you do some index calculation. You have like, just consider how many for loops there are. These are all assembly where you have to count on these iterations. They cannot stay in registers. They have to be somewhere on the stack. You have to add to that, store it back to the stack, do the compares, do the jumps. And every time an inner loop is done, it's a branch misprediction, because it's long as it's looping, it's predicting to go back and loop. And at some point it's predicted to go back and loop, and then it determines, oh, I need to go out. And every time you go out, it's a branch misprediction. And all these, of course, cost. So in terms of perfect parallelism, you have it in the inner loop, but then your Amdahl hits and you have these parts of serial stuff that happens in between that you cannot get rid of. And so you have this perfect parallelism in there, and there's some bound on that. And how you can improve on that bound is hard to theoretically pin down and calculate. All we know is the upper bound is 32. We can't get above.
Yes. Okay. Yeah. Yeah.
So since this sounds extremely similar to what I know about GPU computing, also coalescing memories.
Yes.
Is there also something like warp divergence where, because of the masks that you mentioned, that do I have to be careful there, or what?
So all of this with SIMD you would do more or less manually, because you do the comparison, you get a mask, and then you do your operations on both sides and blend, or you apply the mask, for example, to a load and store. But definitely, yes, you can have this kind of situation. And that's what I mentioned. If you want to have this select function, You have to just compute both sides. And that's this warp divergence in a sense, right? Because that divergence means you have to compute both and then blend the results. Yeah.
But how does it compare to existing libraries like MKL? I mean, my question is more...
yeah, I have not tried them on these laptops, so I don't know. And this is not...
You expect it to be just an abstraction on top of what they have manually tuned?
So an implementation from a vendor, I would assume they go down to assembly at some point. They do not want to depend on the compiler doing something different in a different version.
How far could they go? Probably in terms of flops per cycle.
So there is an optimization that I did not do here that you can think about, and that is further optimization of caches in terms of streaming operations. So you have the ability to tell, I'm going to read this cache line once and never again. Like you load it and you forget about it, and then you can replace it with the next thing that you ever need. Because whenever the CPU needs to decide I need to load a cache line, also needs to decide I need to throw away one, which one to take. There are some heuristics, there are some protocols what to do. And if the program knows and can tell by marking them like I read this and I never need it again, then it can be more efficient in terms of these cache operations. Similarly, you can have stores where you can say, now I'm storing to C. I'm not going to see these anytime soon. I'm going to work on other stuff. Whenever you store it, just store it further down in the cache hierarchy so that this is free for other stuff to load. So these kinds of streaming optimizations, I worked on them at some point and they can also improve some of this. So some of the waiting times that happen just through the memory subsystem, you can certainly think of, I could get rid of some of them still. It gets really involved there. You would not, the main algorithm of the matrix multiplication starts to go away, right? This is starting to just become architecture. You're just seeing through every part of the architecture here. And of course, this is bad in a sense. But then again, you would try to write these things as low-level implementations of a API that then is completely oblivious to these things. And then the user would just see, okay, I'm having my stib-linear operation on an empty span, and it just does that. But underneath it's all these kinds of architectural magic that nobody understands except a few people who study CPU architecture and all kinds of offsets. The theoretical limit on the actual flows and operations, I would have to think through the actual loads and stores. I have not done this recently. So how many loads per floating point operation, how many stores per floating point operation, and if there's anything limiting there, there's an upper bound of how many floats you can do, right? Because you see, you always have to load from A, B, and C, because we have to accumulate onto C. If we were only loading from A and B and then storing to C, our ratio in terms of loads would be better. So figuring out what is the ratio of floating point operations to loads here would be interesting. Whether there is an inherent limitation so that we cannot get to peak flop, and if there is something potentially that could be done to reuse some of the loads and keep them in registers. Also, you would want to look at the disassembly. Like I said, if the compiler ever decides to spill a register onto the stack, we lost. Because it's another load store that just gets in the way. And we're on matrix multiplication. We're doing peak flop performance in terms of the FMAs. We're just limited on the loads and stores.
Okay. Let's thank Matthias for these 3 days of C++. It was amazing.
Thank you.
In 20 minutes, we have a seminar. in building 40. She's in front of restaurant 1. Not saying we should run, but I should run.
It's 10 minutes of fast walking.
Yes.
Upload your solutions to the CMD Hello World somewhere?
Yes.
It would be good
Yes.
to see them, because I'm very stuck in generating.
Yes, I will
from the
try
CMD stuff.
to get to that as soon as possible, which may take some time, but yeah, yeah.